The following message is best viewed on an oscilloscope.
Okay, thank you. Good morning, all. Welcome, everybody. So this dark matter session will mainly focus on different experimental techniques. So we have a lot of exciting talk. There will be 20-minute talk, a 5-minute question. The time for the question might not be enough. That's why we have some speakers have prepared some private room session that will be at the end of the talk. Coffee break are meant to discuss if you wish. The full conference is recorded, but coffee break are not. We will post the recording. There are as well the Mattermost chat if you want to send question and so on. For question, we usually use raise hand on the Zoom, or you can write your question. If you can't speak, you can write your question in the chat, and we'll do the question for you. Please unmute yourself if you're not talking, and let's move ahead. So this is pretty much all the technical details. So the first speaker of today is Yuri Fiaschi from Münster University, and he's going to talk about MEV neutrino dark matter, relic density, lepton flavor violation, and electron recoil. So Yuri,
okay.
So we will keep the video on, and I will annotate when you have 2 minutes left over the 20 minutes.
Okay, I think you can all see the screen.
Yeah, that's perfect.
Fine, okay.
Thank you.
Yeah, thank you at first I really want to thank the organizer and the chairs for setting up this virtual conference, which I can only imagine how much effort you needed to organize such an event. So really, thank you. Okay, I'm just going to talk today. This is the topic of my talk, MEV neutrino dark matter, and I will focus on various observables from astrophysical, collider, and so on. So these are the topics of the talk. I will introduce the model that we will analyze. That is a variant of the SLIM model. Just going through some motivations and the phenomenology of this model. We will see what are the effect of experimental constraints on the parameter space of the model, constraints from all the various kind of experiments, collider, cosmological observation, neutrinos experiment, lepton flavor violation, etc. And lastly, I will also comment on the possibility of constraining the model using novel techniques based on electron recoil in direct detection experiment, namely the Xenor 1-ton experiments, and then I will conclude. So very quickly going through motivations. Well, there is not much need to motivate why are we studying dark matter. There are several evidences for the presence of this elusive particle. We have gravitational lensing, the rotation curves of galaxies, and observations from Planck satellite and WMAP and COBE before that. In the end, we are able to set to measure the abundance of this dark matter particle in the universe, which constitutes about 26% of the energy content of the universe. Another BSM physics evidence that we have is related to the existence of neutrino masses, of small neutrino masses. Okay, so from oscillation, we measured the oscillations of eigenstates of neutrinos, and we can only we can interpret this observation by giving a small mass to the neutrinos such that they would oscillate between the mass eigenstates in their interaction basis. These two evidence for BSM physics can be addressed together by this class of models that are called minimal models. So these minimal models, they introduce a minimal amount of BSM fields. Namely, they are classified adding less than 4 scalar or fermion multiplets, which can be either SU3 color singlets, SU2 singlets, doubles, triplets, and so on. Generally, also an additional Z2 symmetry is introduced to stabilize the lightest Z2 odd particle, which plays the role of the dark matter candidate. And in these minimal models, it's very interesting that the two sectors, the dark sector and the neutrino sectors, are connected together. So the neutrino masses are realized radiatively through the new interaction that appear once the dark sector is introduced. And there are several examples of these kind of models that have been studied in the past. The most famous probably is the scotogenic model, but there are also some others that you can see here, listed here. So the first question is, why do we want to study dark matter? Especially, particularly in this model, we will see that we will naturally end up with a very light dark matter of the order of the MeV. While generally GV to TV dark matter is considered in order to explain Rayleigh density and astrophysical observation, there are also strong motivations to study also the MEV, much lighter dark matter, so around the MEV scale. Mainly, with this choice, we can address some astrophysical problems, which are missing satellites, galaxies, the too big to fail problem, and the core problem for inner dark matter density profiles that are listed here, and you can see here what they are related to exactly. So what we do in this, we did in our work is to consider this SLIM model, which stands for scalar as light as MEV. And in this model, the matter content of the standard model is augmented by adding one complex scalar singlet. This is a slight variation on the original SLIM model. The original SLIM model actually considered only a real scalar singlet, while in this, in our work, we choose a complex scalar singlet, and we will see later why, the reason of this choice. Then we also add two singlet right-handed neutrinos this will play the role of right-handed neutrinos that have this twofold purpose. The first one is so the lightest will be of the order of MEV and will be our dark matter candidate. And the two generations are necessary in order to generate radiatively the neutrino masses. So this right-handed neutrino will both provide a dark matter candidate and will also generate neutrino masses radiatively. And on top of that, we also add one complex scalar doublet in order to restore symmetry at high energies. This is the Lagrangian of the model. Some terms are highlighted, namely we have in red the right-handed Majorana neutrinos. As we said, these they are introduced for this twofold purpose. Then we have this term that is underlined in blue color. This term is introduced to softly break the U1 symmetry into a Z2 symmetry, which means that basically this parameter M4 has to be small. And this, again, the Z2 symmetry eventually will be used to stabilize the lightest Z2 odd particle, which will be our dark matter candidate. Lastly, this term that is underlined in green will be very interesting for the phenomenology of the model, because it is telling us that the model is mostly leptophilic, which means that we have a coupling between the new introduced particles, the right-handed neutrinos, and the complex doublet. these are coupled to the standard model leptons. So both the coupling with neutrinos will be responsible for generating the masses radiatively, while the coupling to the charged leptons will be responsible to some other interesting observations like the lepton flavor violating processes. Okay, in this model, after electroweak symmetry breaking, we have the new charged scalar particles acquire mass, while the neutral components of the doublet and the singlet, they mix together, and the mass eigenstate can be written as shown here. And you can see that their mass differences can be fine-tuned to be small. We parameterize this small splitting by this parameter epsilon. And if we choose this epsilon small enough, we will be able to explore MEV range for the masses of the of both the lightest new scalar particle and the right-handed neutrinos, which will be the dark matter. Now I will move to the to impose the experimental constraints on the parameter space of the model. Namely, so we have various several constraints from the Higgs potential. For example, these constraints, they fix the couplings lambda 4 and lambda 5, and together with, and also the lambda 6, these are related to the mass of the new charged particles. And this mass is strongly constrained by collider measurements on the branching relation of Higgs into two photons. Indeed, the new charged scalar particles, they will enter in the decay of the Higgs into two photon in the loop. So from the measurements on the branching relation of Higgs into two photons, and also on other constraints from LEP, which set the masses of the scalar particles, of these BSM scalar particles above a certain threshold, which, if I remember correctly, is about 95 GeV or so. So with all these constraints, we are able to bound the parameters lambda 4 and lambda 5 that we set to about 0.1. So with this choice, the Higgs sector and the masses of the charged particles satisfies the experimental bounds. Cosmological constraints instead require, first of all, they do require that the singlet and the doublet mass must be close to each other in mass. So there has to be a relatively small mass splitting between these particles, because this way the dark matter, the relic density, the dark matter that is provided in this model does explain, is able to address all the cosmological problems that we mentioned earlier. So missing satellite galaxies, cusp core, and too big to fail problem. The other couplings of this that appear in the Lagrangian, lambda 2, 3, and 7, they are related only to processes that convert dark matter particles into other of the new BSM particles that we added. So anyway, they do not have too much phenomenological impact. So we just fix them to some values that are suitable for our purposes. Again, we said that M3 has to be not much larger than V for the reason that we said above. And anyway, what we do, we fix the remaining coupling lambda 2, and we vary instead this parameter epsilon. Finally, as we said, since the masses of the scalar and the lightest right-handed neutrino has to be close to each other, we scan we scan their mass ratio between the range 0.1 and 0.98. Finally, the constraints from the neutrino sector these are taken into account by means of the so-called Casasibara parametrization. So through these clever parametrization, we are able to translate the constraints from neutrinos measurements into constraints on the parameter space of the model. So basically, it's just a redefinition. So the neutrino masses are obtained through the expression that you can see here, which comes from the diagram, the loop diagram that you see above. So this is the diagram that is responsible for the masses of the neutrinos. And by inverting this relation, we are able to set constraints on the lambda 8 parameter, starting from measurements in the neutrino sector, so the PMNS matrix and the mass and the absolute difference in the masses of the neutrinos, which is also something that is measured experimentally. And everything comes out. So basically, after applying this parametrization, once we put we give as input the neutrino measurements, we automatically obtain a lambda 8 parameter that generates the correct masses of the neutrinos as well as their mixing. So we immediately recover their masses and the PMNS matrix. So all in all, basically we have a long list of parameters, and we have performed our phenomenological study using this chain of tools. So we implemented, we wrote the Lagrangian in a specific form that is useful to as input in SARA. With SARA, we have been able to generate Feynman rules and Spheno codes and micro-mega codes that can be compiled. Spheno is used to generate the spectrum of the model for each parameter space point, and also to calculate some of the low energy observables. And with micro-mega instead, we use it to calculate the relic density for each parameter space model. The first observables that we checked was the relic density. As you can see in this model, we can obtain a really large, we can obtain relic density in a really large range. However, you can see this blue line in the plot in the top left. This one sets the exactly the relic density that is measured by the Planck collaboration. And if we project all these parameter space point on this line, we can see that we still have a reasonable number of parameter space points which satisfies the relic density constraints. And you can see that the range of the dark matter particle, which is our lightest right-handed neutrino, can go from a few MeV up to about 10 GeV. So in this model, this is the range of dark matter masses that we explore. The next observables that we took into account is the lepton flavor violating constraints. So as I said, since the new particles, they couple to the charged leptons in the standard model, we have some contribution to lepton flavor violating processes. Here we consider first the constraints from MEG experiments on mu to E gamma, in the conversion mu to E gamma, but very similar constraints can be obtained if one considers other lepton flavor violating experiments, such as the conversion mu into 3 electrons, or the capture of a muon in titanium going to electron in titanium. Anyway, you can see that these solid lines, they in the plot, they correspond to the current limits, while the dashed line is just a projection of future limits. Anyway, you can see that basically the imposing lepton flavor violating constraints on this particular observable strongly constrains the parameter space of the model, mostly actually this lambda 8 parameter. You have the lambda 8 coupling to the electrons in the x-axis, and in the color scheme instead you have the coupling to the muon. So basically, from these constraints, this lambda 8 coupling is constrained to be below 10 to the minus 2 or 10 to the minus 3. And future measurements will increase these bounds by roughly a factor 4. The last constraints that I want to talk about concerns the possibility of detecting the interaction of dark matter particles with electrons in direct detection experiments. So this is quite a novel thing. Generally, yeah, thanks for 2 minutes left. Generally, one would consider the scattering of dark matter particle over nuclei. But since this model is particularly leptophilic and the dark matter is particularly light, we have perhaps more chances to observe the recoil of dark matter particles on electrons. So the diagrams that are responsible for this process are drawn here in the top right. And what we did is we performed a feasibility study considering the sensitivity, after some consideration on the sensitivity on the xenon 1-ton experiment. So the ionization rate can be written like this. And in this expression, there are several factors that enters. We have particle physics. Particle physics enters in this dark matter electron cross-section, which will be calculated from the 2 diagrams above. We have nuclear and atomic physics, which enters in these 2 factors that I highlighted in green. We have ionization form factor and a correction for the wave function of the escaping electron due to the fact that we have some screening of the charge of the nuclei. And finally, we have astrophysics quantity that enters in this eta, which is the mean inverse dark matter velocity. I have more details on this later on if you have questions. So basically what we wanted to do first is to consider which is the size of dark matter electron cross-section that we would expect in this model. And here we show which kind of cross-section we would expect for dark matter masses around the MeV scale. And as you can see, even for very large lambda 8 coupling, and with very large, I mean, we cannot go above 10 to the minus 2. Still, the cross-section, the dark matter to electron cross-section does not go above 10 to the minus 52 centimeters square. And this is extremely low value. Indeed, it is actually several order of magnitude, like 10 order of magnitude above the most optimistic projection for sensitivity in this direct detection experiment. In our work, we actually discussed extensively the possibility of improving the sensitivity of xenon experiment in this very low dark matter mass region for their sensitivity regarding the scattering over electrons. However, after some discussion and the possibility of reducing the signal, I mean, instead of considering the coincidence of the 2 signals, S1 and S2, given from scintillation and ionization signals, we thought about the possibility of considering only just one of the signals, the S2, because it has a much lower energy threshold. But even in that case, we still have a quite high background that we cannot reduce. And even in that case, with such a high background, the limits, the sensitivity of the experiments just drops down. And these ranges of cross-section is difficult to, will be really hard to observe in the future. Anyway, this drives me to my conclusion. I think I probably am running out of time, so I will just leave it here and for you to read it and wait for questions if any. Yeah, thank you
very much, Yuri. We have a few minutes for quick question, if there are any. If not, you might want to read the conclusion.
Okay. Okay, I will read the conclusion. Meanwhile, people maybe they come out with some questions. So the summary of the talk just is highlighted here. We have considered a variant of the SLIM model with where in this minimal model we have right-handed neutrinos which play the role as dark matter candidate, and with the addition of some interaction of some new particles that we have included in the model, we were able also to generate neutrino masses radiatively. The lightest right-handed neutrino, which plays the role of dark matter, comes out naturally with a mass of the order of MeV to GeV. By fine-tuning with a small fine-tuning of the parameter of the models, we were able to reproduce the correct relief density, and we have imposed in the parameter space of the model constraints from all the other experiments, colliders, lepton flavor violating, etc. And finally, we also studied the possibility of detection of this model in direct detection experiment through scattering of dark matter to electrons, which is a novel and recent development of this kind of experiments.
There is a question from Kalpana.
Yes, please.
You would need to unmute yourself.
Okay.
Okay, thanks.
Yes. Hi. Hello. Can you listen? Can you hear me?
Yes.
So I have a question. That is the dark matter. Is it a mixture of the right-handed neutrinos and the scalars?
Yes. Yes, indeed. The mass eigenstates. I have it here. Yes. Sorry. So we have in the model we have two scalar. We have the scalars, the doublet, the new doublet that is introduced, which mixes with the Higgs and the scalars and the complex singlet that we have introduced. So
Higgs
we will.
And the complex singlet.
Yes.
Okay.
Yes. So basically, this mu parameter mixes the new scalar doublet, this eta that we introduced, with the Higgs, which is this capital phi, and this rho, which is the scalar complex singlet. And these they mix together, giving rise to a light scalar, actually two light scalars, one real and one imaginary, and two that are heavier. The two lights, the light scalars are necessary in order to satisfy, to address for the cosmological problems that we mentioned in the beginning. They have to be light. They have to be, so in order to address this issue, this scalar has to be close in mass to the lightest right-handed neutrinos, which plays the role of the dark matter. I hope this answers your question.
Okay. Thank you, Yuri, again.
Okay.
So, Katerina, would you like to introduce the...
Okay, I can stop sharing.
Yes, thank you.
Yes. So we have now the next talk. And it's, if you can start sharing the slides already. It's about the scintillating bubble chamber for dark matter and also reactor CE new NS. I hope I pronounce it correctly. So this is Pietro Giampa from Triumph.
Hi, thanks for the introduction.
Of course.
Okay, yeah, I'm very excited to talk about the scintillating bubble chamber, or SBC experiment. I hope everybody can hear me. I have decided that I will, that I will skip the general math introduction and talk directly about the SBC overall strategy and kind of why are we doing this and kind of what is the plan for SBC. And then I'm going to talk about the SBC experiment itself. And then give a quick update on what the current status and timelines are and wrap it up as conclusion. So let's jump straight in with the SBC strategy. In order to talk about SBC, I really have to talk a little bit about how bubble chambers work to begin with. And so if we look at the top left plot, if you take a standard fluid, you're going to sit somewhere in the pressure versus temperature parameter space, like this blue dots here. In your liquid phase, and that corresponds to a Gibbs potential that is shown on the right-hand side with one single settle point. But you can imagine that if you can bring the pressure down very slowly, say from the blue point all the way to the red point, you move from the liquid to the vapor phase, but you don't actually change phase. So you remain in a fluid state, and you're now in what it's called a superheated fluid state. And the corresponding Gibbs potential on the other side for the blue point now becomes the red line, which has two settle points, one lower. And that's quite important because if we have a particle interaction with the superfluid, we know that energy deposition in any material leads to either, many mechanisms, whether it's scintillation, ionization, or the formation of heat. If heat is well localized, you can actually make the transition from liquid to gas phase and therefore undergo nucleation or forming bubbles. And that's quite important because the heat is to be fairly localized to do so. And we know that there is a big difference in the EDX between nuclear recoil and electronic recoils. And so if we can tune the so-called threshold, meaning if we can tune the pressure which we operate in order to maximize this settle points difference, we can then operate at threshold such that we're completely blind to electronic recoils because they don't have enough local heat to overcome the minimum threshold to generate a bubble. And so those little detectors have become extremely useful lately for low background application, and PICO is one great example on the right-hand side. But then if you think about turning the fluid into a liquid scintillator, say for instance, if you take a liquid noble like argon or xenon, you get the benefit that a fraction of the deposit energy by the particle also goes into the scintillation mode, which you can then use to interpolate more physics. And that's really the overview of SBC. The plan is to combine the electron recoil discrimination of bubble chamber with the event by event energy resolution and low threshold liquid noble detectors. And what I mean with that is the bubble chambers in low background techniques are particularly good because of the tunable threshold, as Pico has already shown that you can operate down to KV values while retaining ER blindness, meaning that your electron recoils just don't have enough localized heat to generate bubbles, meaning that you have a whole set of backgrounds that you just won't see in your detector with millimeter scale position resolution, and Pico has shown this is a scalable technology. And so if you switch to a scintillating bubble chamber, what you gain is that you can actually push your threshold to much lower value, all the way down to the tens of EV, while retaining ER blindness. And this can be seen in the plot to the right, which shows the probability of forming a bubble from a typical electron recoil on the y-axis versus threshold on the x-axis in KV. And then you see those are the standard limit plots from electron recoil stimulation from Pico. And I'll mention later that collaborators in SBC have operated a liquid xenon bubble chamber, demonstrating already that you can push down to much lower thresholds with liquid argon, while retaining ER blindness and millimeter scale position resolution because of the imaging. But you also add calorimetry now through the scintillation process and you have a scalable technology, as I mentioned. And those properties are actually really good for two types of searches. So you can perform a very competitive low mass WIM search, even with just 10 kilograms of liquid argon. So if you build an SPC detector or a liquid scintillating bubble chamber on the scale of 10 kilograms here, you can already perform a pretty competitive dark matter search, carving even a complete new free set of parameter space in the standard spin-independent WIMP nuclear cross-section as a functional WIMP mass parameter space. And that's our plan for operations at SNOLAB. But it turns out that those kind of detectors are also extremely good to do precision measurement of coherent elastic scatters of neutrinos on argon and xenon. And so we're interested in, for instance, studying reactor neutrinos with this. And here's an example of the rate above threshold as a function of recoil energy, recoil threshold. For the currently, we're working with UNAM to identify a new site for this. And so we plan on building two identical detectors with minor tweaks to optimize for the independent research, one for dark matter and one for neutrinos. And we're going to be doing this in phases. It's actually multiple phases. So the first phase is what we call SPC Fermilab. That will be operating in Chicago at Fermilab. And the plan is to build and commission a first detector really to study the threshold effect. In parallel, we're planning to build an identical detector with just a little bit more attention paid to low background material selections and maybe some minor tweaks at SNOLAB to complete a low mass dark matter search. And then finally, the plan is to dismantle the detector in phase one, so SPC Fermilab, upgrade it and move it to a reactor site for the study of coherent elastic scattering neutrinos. And we're currently considering the Laguna Verde site in Mexico. So this is really what we're doing with SPC, what are our goal and what is our plan. So let's talk a little bit about the experiment itself. We have a collaboration that is shown here. This is mostly a combination of Canadian, US, and Mexico effort. And you can see some of the names here you might be able to recognize with the impossible to miss these days picture of a Zoom collaboration meeting, which is a must. So what has the collaboration achieved so far? Where collaborators at Northwestern universities have operated this liquid xenon bubble chamber, which you can see a picture of the chamber here on the left-hand side. This is a very xenon bubble chamber, but they were able to operate it down to 500 electron volts in threshold, despite having only 30 grams of mass and a 0.3% overall photo collection efficiency. And they were able to see interesting events, like for instance, this bubble, and they were able to spot the scintillation light from the neutron-induced bubble, and followed by the acoustic signal, where the difference really lies in the speed of light and xenon. And so they were able to demonstrate that you can push the threshold really low. They didn't see any evidence of nucleation from electronic recoil, and they were able to test with a neutron source fairly well the nuclear response as well. But that was just a test. The next phase, the next part of the program, is to use liquid argon, is to create a liquid argon bubble chamber and try to operate it down to 40 electron volts with a total mass of 10 kilogram. And we're planning for an electron recoil background of about 1 bubble per ton here. And we'll see in a minute that we have a overall photo collection efficiency of 2%, so a large improve compared to the demonstrator. So here's what the detector looks like. For those familiar with bubble chambers, is the so-called right side up geometry that you may have seen from Pico lately with a thermal gradient. The liquid argon itself is contained within 2 fused silica jars, an outer jar that you can see here at the rim, and then an inner jar shown down below here. The inner jar is actually controlled by an hydraulic pistons that allows us to pressure cycle the target and bring the liquid argon into superheated state and then repressurize and depressurize again in multiple cycle of between 20 to 360 psi. Any events that occurs within the liquid argon will be visualized by the cameras above. The scintillation light is measured using silicon photomultipliers that are spread across the jar. And we're also listening through piezoacoustic sensor to the bubbles. I should mention that the liquid argon is actually spiked with about 100 ppms of xenon. This is primarily to shift the scintillation light from 128 nanometer peak to 178 nanometer peak in order to be a little bit more friendly with the transmission of the jar. And as I mentioned, with a liquid argon target, it comes the difficulty of doing this in a cryogenic environment. So the entire detector is placed inside a pressure vessel, which sits inside a vacuum jacket. I also want to highlight that there is a thermal gradient within our detector. So you can see that the bottom is actually set at around 90 K, while the top is on the order where the main target is on the order of 130. And this is really done because we want to make sure that we can operate the target at the top in a superheated state, but the bottom side of the fluid will not be in a superheated state even after decompression, so that we don't get pathological events from the bottom. And to better visualize how we do that, that thermal gradient, I wanted to show you an engineer rendering of the actual detector, just to show you that things are not just sketches. Here you can see kind of the condenser and the cooling head that provides the liquid argon. And this is the cooling band that allows us, which is liquid nitrogen fed, that allows us to keep that thermal gradient from where the jars are and the SIPMs, as you can see here, to the rest of the compression system in the detector below. I want to spend just a little bit more time talking about the readout system. I mentioned briefly, but let me go back and explain a little bit more into detail. So if you look at our detector at the very top, and you can see here the housing light out here in the top left, we have 3 high-speed cameras on the order of 100 fps and a resolution of 1 megapixel that are used in combination with IR illumination to image the bubbles in the chamber. Then alongside that, we have 32 Hamamatsu VV4 quads, silicon photomultipliers that are spread across the outer jar, as you can see here, wraparound reflectors material completely across the jar, and allow us to detect the scintillation light emitted by the stimulation of the liquid argon, all the way down to a 5 kVNR estimated nuclear interactions. And finally, we also want to listen to the bubble. So we have 8 piezos transducer laid out across the jar at the bottom. Those are quite important because as we have learned from other bubble chamber, the ability to listen to bubble enable us to decouple particle IDing within the nuclear recoil definitions between neutrons and alphas. So one natural questions that you might want to ask yourself after seeing what the detector looks like is how low in threshold can SPC really go? So this really becomes a threshold game. And so we know that historically, we know that electron recoil, can lose up to 10% of the deposited energy through heat. This actually mainly occurs just after the recombination in the simulation for argon and xenon particularly. And this seems to be consistent with historic results of liquid argon bubble chambers observing tracks on the order of tens of electron volts in threshold. Now, one of the things that it's quite important to mention is that thermal fluctuations have to be extremely well understood in order to pin down and understand processes at the order of tens of EV in threshold. And what I mean with that is that you really need to understand the boundaries of your first continuum, which is shown here on the plot on the right. To really understand how localized your heat distribution in per ER interaction is. However, with a current understanding of thermal fluctuation at threshold, we expect the SPC detector to be able to run with a background of 1 bubble per turn year from electronic recoil interactions at a threshold of 40 EV. For liquid argon. And I should mention that the very purpose of SPC Fermilab is to stress test this and really study this very precisely. And so to do that, we need also a calibration plan for this study as well. And this is really where the beryllium-9 photoneutron source comes about. There are some challenges, obviously. We're limited to the number of bubbles per day that we can generate simply by the compression rate in our chambers. And we want to make sure that we have a source that we can also extrapolate good information from the SIPM's coverage. So we decided to go with this beryllium-9 because being a photoneutron source allows us to really not be swamped by gammas, like most standard MB sources really are. And our plan is obviously to study neutrons interaction and gammas interaction separately. So we wanted a source that will enable us to decouple that. So that's our plan. What is the current status? So we're not just designing stuff or planning stuff anymore. We've been building stuff since the beginning of the year. So one example is that the electronics, for instance, for the photo readouts are completed now in Fermilab. You can see the various components of the inner assembly of the detector are already ready and have been tested at Fermilab, like the piston shaft, like the pressure vessel, the vacuum jacket. You can see here the pressure vessel being tested outside of Fermilab. The process system is being built. Obviously, things came to a stop with COVID, but nevertheless, we're now slowly being able to start making moves again. So here's what our plan and tentative schedule going forward is. Please take this with a grain of salt, as we are all trying to understand the impact that the pandemic has on our schedules. So we're gaining access and to laboratories and access to different spaces. So we're trying to learn more, but obviously keep in mind that the schedule is very fluid as we're all moving forward. So our plan is to continue, now that we're getting access to some of our construction site, to continue the SPC Fermilab construction, which started earlier this year, with the goal of finishing in the first trimester of 2021, followed immediately by the operation of this SPC Fermilab detector, really with the goal of studying events, neutrons, nuclear recoil, and electronic recoil at threshold, and understand the impact of thermal fluctuations to a threshold. In parallel, starting in the last trimester of 2021, we want to start building the SPC SNOLAB detector on site, and some preparation for that obviously have already started. And we have taken the opportunity of the, let's say, break that we have taken from SPC Fermilab construction due to the pandemic to start fast tracking some of the processes for SPC SNOLAB. The plan is to complete the construction by the last trimester of 2022, and then start the operation with a first dark matter results to follow shortly. And then in 2023, the plan is to repurpose the SPC Fermilab chamber into the SPC 7's chamber for the study of Coherent elastic neutrino neutrons scatterings at the reactor site in Mexico. So I might be a little bit ahead of time, but it's probably for the best. We're getting a little bit of time back. So let me draw some conclusion. Hopefully I've shown you that scintillating bubble chambers provide a unique technique for low mass WIMPs detection in a scalable option with ER blindness, given low thresholds all the way up to 40 eV. We're planning on doing very detailed calibration studies for a liquid argon bubble chamber after some of the collaborators have already tested a liquid xenon bubble chamber at Fermilab, which we expect to start in 2021. And we're gearing up for our dark matter study at SNOLAB by late 2021, where we anticipate starting the construction of the detector with first results by 2022. And obviously, we're investigating also the possibility for a site reactor so that we could also study Coherent elastic neutrino scatterings. And we're narrowing down to a site in Mexico, Laguna Verde. But I also wanted people to keep in mind that we're also thinking about a potential ton scale SPC SNOLAB or something on the order of ton scale to get us all the way to the neutrino floor for dark matter searches in the low mass WIMP as well. So we're a very energetic collaboration and always looking for new members. So if you're interested, feel free to ping any one of the members that you've seen on the collaboration slide. And with that, that's it for me, and I'm happy to take questions.
Thank you very much. That was a very interesting talk. It's nice to see that there's a lot of effort for the low mass side of with dark matter. Is there anyone who has questions? I think I see many. That's great that you were, but we can take them. So the first hand up I see from Craig Dukes. So you can unmute yourself and speak.
Yes, I have a question about how often do you cycle this bubble chamber? I'm not quite sure I got that.
So for cycle, we really repressurize the chamber every time we have evidence. Well, every time we see we trigger the chamber. So it really will depend on which mode you operate with and at what. And if you're running with some calibration mode, at which source you're using, but you're bounded to even at if you would constantly recycle, you're bounded to up to 1,000 cycles per day, just to give an idea of the length of the cycles.
How far can you go between cycles?
That's a very good question. I would have to go back and think about it before I can give you an answer. Sorry about that.
Thank you.
Then we have, in order of hands, Adrian Di Giovanni.
Yes, thank you for your talk and great idea and beautiful detector. So I was thinking that since you are actually considering of doping the argon with xenon, actually I don't remember the exact number, but there is sort of magic number for the concentration that actually increase a lot the infrared emission. So you could even exploit this channel in order to recover a bit the light collection. And of course, then you need to also add a proper detector. But since you are using our liquid argon doped with liquid xenon, so I think it's worth investigating this possibility.
Yeah. Thank you very much for the comment. It is an extremely valid comment indeed. We are aware of the IR emission, especially after in argon after xenon pollution, and so we're actually undergoing we're about to start a more detailed study of the xenon doping with a few other collaborators and some out of collaboration members in order to understand exactly, as you said, where the correct balance is in between maximizing 178 nanometer light and IR light. So yeah, thank you very much for the comments. Very well taken, and we'll study that for sure to optimize that.
Thank you. And then we have a question from Ablet.
Okay, thanks, and this very interesting experiment. So, just a simple question: how do you distinguish between the events from the dark matter or from wind compared to the events from background?
Right. So in that respect, it becomes very much like any dark matter search. In say the plot that you see really on the bottom right hand side. So it really becomes a matter of modeling your background extremely precisely, and then look for deviation in your background model in the parameter space that you expected WIMP interaction in your detector. So you really, it really becomes a counting exercise. And then depending on, if you do see a signal, depending on how intense that count is, you can reconstruct then properties, basic properties of a potential signal like mass and intensities, or I guess local densities.
Okay, so in that case, for example, for the data taking, how long are you planning to run the detector? Like several years?
Right. So yeah, exactly. So you expect, I would say, at least a couple of years of operation. There's obviously you got to walk a line between maximizing your exposure and whatever your funding allows you to do, obviously. But yeah, we're talking about multi-year program operations.
Okay, thanks.
No worries.
Then we have one more question by Paul Mother.
Yeah, hi. Maybe you've said it, but the superheated state, how stable is it? Do you have to keep the pressure really, really tight, or is it a lot more stable than I imagine?
So again, they're really this really goes. I assume you're obviously talking about operating at as low as threshold as you can go. So that's really what we're planning on doing with SPC Fermilab. So we want to understand exactly the stability and the performance at our target threshold of 40 eV. And that includes also the ability of our system to deliver a stable operation at that particular threshold. So we know from other bubble chambers that the stability at threshold is very good, and the operation at threshold is very good. But as I mentioned in liquid argon, we also have to deal with internal physics that are currently unknown, like thermal fluctuations and so on. So we're planning to study that very methodically all the way down to the 40 eV. But remember that the beauty of this detectors is that you can always change at what level you depressurize to run at higher thresholds if you want. So if it turns out that your threshold, for instance, I'll give you a random example. Say you're running a liquid xenon bubble chamber. It turns out that your threshold at 200 eV is too low and it's not stable enough. You can always operate at 300 and so on. So it really becomes then a game of where you set your threshold. But we're hoping that at 40 EV we're confident that at 40 EV we should be able to operate stably.
Thank you.
No, welcome.
So thank you very much. A round of virtual applause for the speaker again, and we can move on to the next talk.
Can I ask a question? Sorry, I can't raise my hand. So, Pietro, what are the background assumptions that you consider for the exclusion plot? It's one bubble per ton year, or? And
the one bubble, yeah. So that's the.
What is the back? So you show the plot, no, for 10 kilogram years and 1 ton.
Yeah, so that's our expected background, which includes contribution from standard component, standard environmental components plus the inner detector components to the best of our knowledge right now, obviously. And that's
the background
on the order
from simulation.
Yeah, and so that's the design. Yeah, and so we use the simulation to tune the design to 1 per ton year.
Okay, I see. Okay, thank you. Sorry. So next, thank you, Pietro. So next speaker is Francesco Pandolfi. So if you want to start sharing the slide. And he is going to talk about carbon nanostructure for directional light dark matter detection. And Francesco is from INFN Roma. So we can see the slide. Thank you.
Yeah, let me unmute. How do you do that? Oh, I was unmuted. Okay, let me share again, sorry. All right. I just had a power cut at my flat 5 minutes ago, so I hope that doesn't happen again during the talk. Anyways, yeah, hi everybody. So yeah, I'll be talking about carbon nanostructures for directional light dark matter detection. I'm going to show you some recent results of the R&D we've done in Rome and Princeton over the past months. So the starting point is this plot. We all know this plot. We've seen it 1,000 times. The exclusion cross-section as a function of dark matter mass. And we also know that to move around in this plot, there's basically 2 directions. There's the vertical direction that you can go down and get better limits if you increase your exposure of your detector. And this obviously typically means large mass. We all know that these limits are all dominated by these multi-ton experiments that we also saw in the previous talks that were mentioned. And then you can also move horizontally in this plot, and that would by changing your threshold, by lowering your threshold, you can achieve better limits moving to the left. So that's the region where we're interested in, the left side of that plot, because in particular the sub-GV region. And there, as we know, the limits are much weaker, up to 10 to the 10 times weaker. And this means that in order to have competitive results, you can actually get away with much smaller targets, even of the order of grams. And to access that region, the reason why all those curves tend to fall off towards the GeV is that most of those searches are based on nuclear recoils, which is limited by about a lower threshold of 1 GeV. And to go down, you have to, as we know, start looking at electron recoils to go down to the MeV scale. And another important thing that we're working on is focus really on directional detectors. Directionality, I mean, to link a possible signal to a region of the sky is very useful, obviously, because we expect the dark matter signals to come from Cygnus, but it's also a way to effectively fight backgrounds. I mean, the neutrino flora that is there in the cyan shade can actually be almost completely avoided at those masses, as it's mostly dominated by solar neutrinos, and Cygnus and the sun never really overlap during the year. So what I will talk about today is detectors which aim for that region and that use solid state targets. And in particular, well, you can do the usual back of the envelope calculation for a classical calculation for dark matter with masses between 10 and 100 MeV. You get that the kinetic energy is between 5 and 50 EV approximately. And that is enough to extract an electron from carbon. The work function is 4.3 electron volts. So then you end up with a recoil electron, which has a kinetic energy of about 1 to 50, say, electron volts. So very soft. And in particular, that electron will have an extremely short range in matter, especially in solid matter. And this is why what we're advocating is that you need, in order to have solid state targets, the advantage of this whole thing is to have two-dimensional materials, such as graphene or carbon nanotubes, because in these materials, the electron is ejected directly into the vacuum. And so you don't have the problem that the electron is reabsorbed in the density of the matter. So let's start with graphene. Here, most of the work is based in Princeton, the stuff that I'm going to show you, and it's shared with the Ptolemy project, which you might have heard of. And if not, there's a talk later today by Marcello Messina in another session, which I suggest you go listen to. Ptolemy aims to measure the cosmic neutrino background and wants to do that with a tritiated graphene target, a very large target, actually up to 0.5 kilogram. And so having to deal with so much graphene, there's obviously a lot of R&D on that. And some of that R&D is also geared, let's say, towards using graphene in dark matter searches. And so the idea here is to construct these graphene field effect transistors, GFET, which basically they're just like a normal FET, but the source and drain are connected by these graphene nanoribbons, which are basically very thin ribbons of graphene, which have a width of less than 50 nanometers. And so this makes them practically a one-dimensional material, and that have very specific electrical properties that depend on this width, W. And so what you see here, what I'm showing is some recent results. So you can see the nanoribbon in question that has produced these results is shown. There's a scanning electron microscope image in the top left. So you can see the ribbon is actually that little line, the vertical line, and it's 3.5 microns long and has a width of 35 nanometers and connects these two contacts, the source and the drain. Now, what you see here on the plot is that the conductance of this nanoribbon varies quite significantly as a function of the gate voltage. So not the source and drain, but the gate, which is at the bottom of the FET. And you have these three regions. There's a conductivity region on the left, which is mainly due to hole conductivity. And there's another conductivity on the right, which is mainly due to electrons. And then there's a region in the center in which the conductivity drops significantly. And that's the charge neutrality point. It happens at charge neutrality. And as you can see, the different colors are different temperatures. And as you decrease the temperature, so you go towards blue, the drop is actually hits very low values. And so you actually get a region in gate voltage in which your nanoribbon becomes not conductive and has a semiconductive behavior. And now when you go close to that region, this has been shown in 2007, this article here, the nanoribbon is extremely sensitive to even single changes in the electronic configuration. And what you see here, this is the blue and the red are absorption and desorption of single molecules of nitrogen dioxide. Every little jump you see there corresponds to one electric charge. And you can see that these are measurable charge jumps in resistivity. They're about 2 to 2.5 ohms. So it's very measurable. So you have a thing that basically is sensitive and can measure the emission of a single, or the arrival of a single electron. And so to use that as a dark matter detector, what you do is just build a lot of them. You have all these ribbons, and you actually, the idea is to put them in this top-bottom configuration, like a sandwich, in which then the two nanoribbons are then also on the two sides. You have these two electrodes. And the reason to have the electrodes is that once the dark matter arrives, it'll kick out an electron, and then the electron will be ejected in vacuum, and then the electrodes will have the function of re-accelerating it back to the detector. So it'll just land in another GFET, some delta X space far away. And so a dark matter event would actually be the coincidence of two cells firing, the departure cell and the arrival cell. And a possible signal will appear as an excess of top versus bottom events when you align this detector to Cygnus. And now the cool thing is that this drift, the electron drift, is completely classical, and you can solve the equations. And actually, if you know the electric field and you know the amount of distance that's been traveled, and you add also time of flight information to your detector, then you have everything you need, and you can solve the equations. And you can fully reconstruct with just these three things the velocity of the electron at departure. And now once you have the velocity, then you can correlate that with the dark matter direction, and there you go, you have a directional detector. So that was graphene. Then let's move on to nanotubes. I'll spend a little more time on that because that's the stuff we're working on right now in Rome. So, okay, nanotubes, you can imagine a nanotube as just a single graphene sheet, which is wrapped up in the form of a straw. And these nanotubes can be grown in labs, and you can actually, with this CVD, chemical vapor deposition technique, you basically can grow forests of vertically aligned nanotubes. And the tubes are typically have a typical internal diameter of 20 nanometers, a length of a few hundreds of microns. And depending on the growth technique, they can be either single-walled or multi-walled, and then they can be grown in different substrates. And yeah, we actually just recently installed a new CVD chamber in Rome. Here you can see the picture of the Rome group happily posing next to it. That had just been installed. It was done thanks to attract funding, and the commissioning actually ended last week. So we're ready to get the first growth going in this week or the coming weeks. And here you can see some other growths we've done in 2019. Here we were borrowing, let's say, the CVD chamber in Trieste at the Elettra facility. And here are some scanning electron microscope photographs. You can see on the left, this is on a silicon substrate. You can see all the tubes, and these are 200 microns long. And on the right, this is fused silica, the substrate here. Again, you can see all these nice little vertical tubes. And these are 157 microns long, and we're not sure, but it might actually be one of the longest growths that has ever been done on fused silica. Or actually, we didn't find much in the literature. So we're pretty proud of these growths, and we're pretty excited to start doing them in Rome too. And if you'll allow me, I'm going to show you another picture because I find these SEM images quite fascinating. This is a little bit more wide angle. You can see the extent, like the size to which we can grow these tubes, and we get decent uniformity all across. We actually have the growths are usually typically 1 square centimeter large. And so how does this work for dark matter? Well, the key idea here is that once you do grow these nanotubes, you get a piece of matter which has highly non-uniform density. And this is shown actually by these plots here. The tubes were bombarded with argon ions, and they were bombarded either laterally on the sides of the tubes or longitudinally, so inside the tube axis, let's say. And you can see here in the plots the results of Raman spectroscopy after these two bombardments. And you can see that in the case of lateral bombardment, the pristine Raman spectrum is already there after only 15 microns of depth. So the damage is contained in the first less than 15 microns. Whereas after longitudinal bombardment, you see that the damage is present throughout the whole length of the tube down to 180 microns. So this proves that the density along the tube axis is much lower than the density and on the lateral side. So this actually works out nicely, at least we think, for a dark matter target, because you would have a target in which the electron, the recoil electron, would be able to escape the target only if it's traveling in the direction of the tube axis. And so this is most likely, obviously, when the tube axis is aligned with the dark matter wind. And so there you go, you have, again, an intrinsic directionality in which you would lose it unless you point it in the right direction. And so the idea, the concept we have is what we call the dark PMT. And you can see it here. It basically, conceptually, it works like a PMT in which you have a cathode on one side. We call it a dark photocathode, in which you have, instead of photons coming in, you have the dark matter wind. They would kick out the electron escapes the tubes if it goes in the right direction, and then it's accelerated by an external electric field. And then on the other side of the detector is just detected by some solid state electron counter, like an APD or something like that. And so the measurement would actually be, you would have these two sets of detectors. You would point one of them in the direction of Cygnus, and then the others in some other orthogonal direction. And then you would look for a significant excess of the ones pointing in the right direction compared to the other ones. And so if you wrap it up and see the expected performance, here you see in the plot, you see the expected cross-section, the excluded cross-section for these two concepts. And so in black, the GFET, and in blue, the dark PMT. This is an exposure of 1 kilogram times 1 year. So, I mean, obviously it's large. We're probably not gonna have a kilogram of graphene, but just to give you an idea. And I mean, here you can see that the two concepts have pretty much similar expected performance. They both peak at around better peak sensitivity around 20 MeV or something, and they reach down to a few MeV. And so if you want to put it, I mean, if you want to compare it to the usual plot we look at, this curve would be somewhere around there. So it would be at the left side of the plot and kind of, yeah, have this shape. So as I showed you, one of the key experimental challenges of this dark PMT concept is that you're going to end up with an electron that even after being accelerated by the electric field, they will have order of a keV energy. And so you want to make sure that whatever you have on the right side of the detector can detect a keV electron with high efficiency. So this is what we've been working on in the past months. The benchmark technology is to use avalanche photodiodes, simply because we have know-how. It's simple, it's cheap, and easy to use. And what we're using right now is these Hamamatsu windowless APDs that have an internal diameter of 3 millimeters. But then we're also considering, as an upgrade, to switch to silicon drift detectors, because they would obviously be a little more expensive, but they would give us ultimate energy resolution for this energy range. And for those, these are the ones we're working at, that we have. These are produced by FBK in Italy, and then the electronics is designed and produced by Politecnico di Milano. And what we have to characterize these silicon detectors, we have a beautiful, actually, electron gun facility at University of Roma Tre. Here you can see this is a photo of the inside of the ultra high vacuum chamber of this facility. You can see here on the right the electron gun, and this is where the APD is facing it, so you don't see the silicon. And then there's a lot of other things that we're not really using this in the results I'm showing today. But I mean, we can do full characterization also with UV light and X-rays and all of that. But for the electron gun, this is a gun which produces electrons, mono-energetic electrons with an energy between 90 and 1,000 electron volts. The RMS on that is below 50 milli-electron volts, so it's really mono-energetic. And we can go down to currents as low as a few femtoamps. So as this is not a bunched source, it means electrons with a frequency, with a rate of about 10 kilohertz or something like that. And also the spatial profile of the beam is very, very nice, because it has a It has a dispersion on X, I mean, a diameter which is less than, say, 0.5 millimeters. So you can actually have it completely contained on the sensitive part of the APD, which has a diameter of 3 millimeters. And what you see here, so some results on the calibration of these APDs with low energy electrons. I mean, APDs are designed for photons. So, I mean, it wasn't completely trivial to use them for low energy electrons. What you see on the left is what happens if you keep the APD off, so switching off the bias, and then just shooting the electron beam all across its surface and reading, so the z-axis is just reading the current which is drained by the APD as you're shooting with the gun. And what you can see is that what we get is a nice little, let's call it electronic image of the APD, in which you're not only sensitive to when the gun is passing over the silicon, but you're actually sensitive to seeing all the electrical contacts that you have around the APD, and you can get this nice image. And then instead on the right is the calibration curve that we get with the APD at nominal bias of 350 volts. And here you see the APD current as a function of the gun current. And you can see that there's a nice, this is the calibration curve if you want. So there's a nice linearity. The fit looks nice. The intercept is compatible with 0. So yeah, this is a nice result. And finally, yeah, I showed you this prototype, the dark PMT prototype. And we actually built one. We called it Hyperion. It's been assembled in Rome, and it's actually, you can see, I mean, here this is a technical design in which we expect to have nanotubes here and the APD over here, and then the electric field between them. And here on the right, you see the prototype, the actual photograph of the prototype, which is sitting in our lab right now, and it's been assembled and it's actually ready for the first tests, which we will do next week or in the coming weeks. Okay, so these are my conclusions. I showed you that carbon nanostructures, they offer exciting new possibilities in searches for light dark matter. In particular, the advantage here is that we're using two-dimensional materials, and so we can minimize the problem of electrons being reabsorbed into matter because they're ejected directly into vacuum. And I showed you these two detector concepts, both which have directional sensitivity. So the GFET made of graphene nanoribbons and the dark PMT made of aligned carbon nanotubes. And yeah, there's been a lot of exciting R&D both in Princeton and Rome. In Rome in particular, we have a new CVD chamber with which we start to, we expect to start growing nanotubes very soon. And the dark PMT prototype, which is ready for the first tests. So here my last slide is just the full list of contributors. And yeah, thanks a lot.
Thank you, Francesco. Thank you for the very nice talk. Are there any questions? Ablet or Ablet?
Ablet.
Ablet, sorry. I didn't know if it was, sorry, sometimes there is first name and last name, that's why.
So I have a few questions. One is if the detector is sensitive to the energy of incoming dark matters, or?
Well, which one? In principle?
Yeah, I mean, if it's just the count and regardless of their, like, for example, if the dark matter comes in different energy, so can you reconstruct the energy of input particles, or?
Well, I mean, right now we're focusing on counting, at least at the stage we are right now. But I can imagine a detector in which if you have, I mean, if instead of an APD here, you have a silicon drift detector, you would be reconstructing the energy of this electron very well. So if you prove that the electron, once it exits the nanotubes, it remembers the energy at the beginning, and that the electric field doesn't spoil that, then, I mean, in principle, it's possible, yeah.
Okay, so the other question is, I'm feeling like this also can be used as the neutrino detector, like you can detect low energy neutrinos, so no. Well,
yeah, I guess the problem, yeah, sure. The the problem with that is that you're still working with very small masses, small targets in terms of in mass. So as long as you're fine with very low efficiency with neutrinos, yeah, I guess.
Okay, my final question is, so the detector works in at normal temperature, right?
Yeah, actually, this is, one of the things that actually I should have mentioned maybe. It's a portable detector and it doesn't need any cryogenics. It does work at room temperature. Obviously, you can squeeze out some performance on this side of the detector if you want to cool it down, but it's not needed necessarily.
Okay, thanks.
And that's actually one of the nice parts of using carbon, that the work function is so large that it's basically insensitive to thermal emission. It's 4.3 eV.
So next question from Paula Collins.
Yeah, actually, I think you got to it with this last question, but this the question about the cooling. If you move to silicon drift detectors, will that change your approach?
No, not really. I mean, obviously, silicon drift detectors, if you do cool them down, you can squeeze out a little bit more performance. But I don't think, at least at this stage, we're more interested in seeing if this technology works, and we're fine with room temperature SDDs. We were actually working on this last week, so it's too fresh to show at ICHEP, but we were seeing some nice performance with SDDs at room temperature. And room temperature right now in Rome means, more than 30 degrees. So.
Next question and last from Andrew.
Nice talk, by the way. So you mentioned mass. I mean, for these dark PMTs, how much carbon is put into this?
Yeah, that's a good question. I don't remember. Is it micrograms? I don't know if Gianluca is online. I remember he was doing these calculations. I think a square centimeter of nanotubes.
1 square centimeter can host up to 10 milligrams.
Milligrams, okay.
I see. Thanks.
So I would like to thank all the speakers of the session, and 10 minutes coffee break, and we will resume at 11 Eastern, 5 p.m. European, I think.
Yeah, so if you have any other questions, so if Francesco Pandolfi is not getting coffee, well, if he is, he can, but I'll try. The connection to Ptolemy is interesting because I remember hearing a talk where they were saying that they're testing multiple different technologies. So is there a timeline and an idea of when they'll choose?
I guess people are taking the coffee break seriously.
Yeah, it's a good idea given that we have a lot. So I'll just ask it on Mattermost. It's easier. So if the next speaker wants ready to try the screen sharing.
Sure, yeah.
Patrick, yes.
Okay, do you see that?
Yeah, that works. So let's see if Rihanna is also there.
Yes, I'm here.
Yeah, okay, so can you try sharing for a minute?
Yes, sure.
So we just get everyone set up.
Okay, so let me check my...
Then we go back to Patrick.
Okay. Sure. Yes, so I think it's working.
Yes, and then we have a small test for Paolo. Okay, Sylvia tells me that Paolo already tested it at the start. So. No need. Okay, so we will start in a minute with Patrick.
Okay, shall I share now? Ready?
Yeah, it's good. Thank you. And yes, if you can, you should share also your video. I can see Patrick already. And I don't know if I saw Adriano, but turning on the video is easy enough.
Sorry, unfortunately, we all get used to this new kind of doing meetings. So yes.
Yes, that works. We can see you as well. All right, I believe it's time to restart the session. I hope everyone had enough coffee. And so it's the turn of Patrick Knight on NewsG, a search for light dark matter with a spherical proportional counter. So the floor is yours.
Okay, thank you for the introduction. Yes, so I just want to talk about the NewsG collaboration, our project, and the search for light dark matter. So I'll talk through the detector concept, our first results, and then a discussion of our current work and our future plans. So first, a little bit of context. We've seen already exactly this this plot, but there's been a lot of effort, a great effort in this region above 10 GeV in the search, the direct search for dark matter. However, the lower mass region is much more weakly constrained, and so this has attracted a lot of theoretical interest and growing experimental interest, as we've seen already in the session. And so we want to explore this region. And so to do that, when we're thinking about the standard nuclear recall from an elastic interaction of dark matter, we need to think about low mass targets, low energy thresholds, and favorable quenching factors. So what do I mean by these? So here in the bottom left graph, I show for a 10 GeV WIMP interacting with several different targets. I've got the recoil energy on the X, and on the Y-axis, some measure of the rate. You can see for a 10 GeV WIMP, then, or dark matter particle, we have favorable rates for heavier targets. However, if we start to talk about lighter matter candidates like 1 GeV, then you can see at the 1 kV recoil energy, then lighter targets such as hydrogen or helium have much more favorable rates. Coupled with this is the need for a low energy threshold. So to be able to see this, obviously we have to have very low energy thresholds. And the other part coupled with this is the ability to see this energy. So obviously not all of this energy is deposited in a manner we can observe in the detector. So for the detector I'll talk about, ionization is the important one. And you can see here for various gas targets that the fraction of energy deposited in ionization is much more favorable for these light targets in light gases. And so this motivates the use of a gas detector, and in particular a spherical proportional counter. So what is this? It's a spherical vessel of order 1 meter in diameter, which we fill with a choice of gas. And at the center, we have an order 1 millimeter anode, which we set a high voltage. So at first order, this gives us a 1/r² electric field in our detector. So if you imagine a dark matter particle interacting in our gas volume, generating some ionization, so some electrons, these electrons drift under the influence of the electric field towards the anode. And then within a few hundred microns of the anode, the electric field becomes high enough that these electrons can induce a Townsend avalanche, and we get an amplification of our signal. And then the drift back of the ions from the avalanche generates a measurable signal we can see. So this is shown schematically or in a cartoon here. And then in practice, this is an example of one of the early spherical proportional counters, which is a repurposed LEP RF cavity. And here is our central readout. In the simplest case, we use a single anode. And so this is shown here. So this detector has various strengths. One of them is that it's easy to make this detector out of radio pure materials. It's just a sphere with some rod here supporting the anode. These can be made out of radio pure copper. The rest of the materials here are all less than a gram, but even so, we endeavor to make these out of radio pure materials. Another thing is the spherical geometry has the lowest surface area to volume ratio, and even with the radio pure materials, the majority of our background comes from this, this copper shell. So in a sphere, we minimize that surface. And the spherical geometry also brings another advantage in terms of the capacitance, and so electronic noise, which allows us to get low thresholds. So the sphere compared to traditional gas detector geometries like the parallel plate or cylinder has the lowest capacity. And also, crucially, the capacitance doesn't scale with the size of the detector. So we can have increasing size of detector without commensurately increasing capacitance. And so low noise and so low energy thresholds. One of the other powers that comes with the detector is pulse shape discrimination. So I said it's single channel readout in the simplest form, but we still have a lot of power with this. So I show here in some cartoons some examples of interaction. So say we have a point-like interaction at low radius in our detector. The primary electrons are in a high field region, so will undergo little diffusion on their way to the anode, and so will arrive at the anode an avalanche within a very short space of time. And this translates to a very short rise time in the signal we'd measure. However, if we had a point-like interaction occurring higher radius, then we'll have more diffusion of the primary electrons, and so greater spread in arrival times translate into greater spread in rise time. Further than that, if we were to have a track of ionization, say, which could be caused by, say, an alpha particle or a muon passing through the detector, then you'd have a much greater range in arrival times of your primary electrons at the anode, and so an even higher rise time. And this is seen in practice here from a test at the surface using a smaller, a 30 centimeter detector with an iron 55 source inside, which is a source of 5.9 keV X-rays. So in region 1 here, we see something like this. This is photons interacting in the gas volume at increasing radius. At some point, they start to interact near the surface of the cathode, or surface of the detector. And then in this region here, cosmic muons, so these are leaving tracks of ionization. And you see these are at much higher rise time. So in this way, with our pulse shape discrimination, we can reject events that are track-like deposits or events occurring near the cathode. And like I said, this is where the majority of our background comes from, this copper surface. So we can discriminate against that compared to point-like interactions, which is what we'd expect for a dark matter interacting in our detector. So for the reasons above, this detector is well suited for a direct dark matter search. One thing I didn't mention is that it's a gas detector, so we can easily vary the gas that we choose to operate with. We can pick light gases which are loaded with hydrogen atoms like methane, or even we could use helium gas to be kinematically matched with light dark matter. I said that it's single channel readout, but actually we're working towards more anodes and higher readout channels, which I'll discuss later. And also, I just want to mention there's many other applications for this detector, such as fast neutron spectroscopy. There was a talk earlier today about that. And neutrinos double beta K, there's a talk tomorrow on that. So I won't dwell on those, but I encourage you to see those talks for other applications of this detector. And this is our collaboration. So we're called NEWSG, New Experiments with Spheres Gas. This was us at our most recent collaboration meeting, which, like many others, ended up in Zoom instead of in Birmingham. Okay, so. And then I just want to discuss our first dark matter detector we built as a collaboration. So this was a 60 centimeter spherical portal counter using NOS-V copper from Arubis, which underwent several stages of chemical cleaning to remove any possible radon deposits on the inner surface. And it's installed in the underground lab in Modan, LSM. So you see it has this overburden here, 4,800 meters water equivalent. This is a detector located inside its shielding, which is layers of copper, lead, and polyethylene. And this is the detector taking out the nice shiny clean copper. And this is our readout structure. So you see the rod and the anode here, which was placed inside. With this this first detector, the first detector we built for a dark matter search, we were able to carry out a dark matter search, and using primarily neon as the target, we were able to place a competitive limit. In fact, the most competitive limit, exclusion limit, 90% confidence level for a 0.5 GeV mass candidate at the time. And this was done with a 9.6 kilogram day exposure. So this was really encouraging for the first detector, and from there we're progressing to the next generation of spherical proportional counter for dark matter searches, which is this one you see here. So it's bigger. It's a 130 centimeter detector. So we have a much larger volume for our gas. It's made from pure copper 4N, so 99.99% pure Rubis copper. And it was constructed in France and first operated for a commissioning run in LSM, but will be installed in SNOLAB, Canada. And we've already had a talk from Deep, but you can see this is where we'll be housed, or are currently housed, in the cube hall in SNOLAB. Another improvement with this detector is an improvement in our shielding. So this is a sketch of the detector inside the layer of 3 centimeter layer of archaeological lead, the 22 centimeter layer of low activity lead, and then around that we have a layer of high density polyethylene. And so I just want to talk a little bit more about the construction of the detector. So this was spinning one of the hemispheres of the detector out of this 4N copper plate. I'm sure, as we all know, copper is a very attractive material for building dark matter detectors, mainly because it doesn't have any long-lived radioisotopes of its own. The majority of the background in copper comes from cosmogenic activation, so things like cobalt-60, but you minimize that by placing it underground. Other backgrounds come from the uranium-thorium decay chains, so they're naturally found in the material and also deposited by radon-222 gas floating around in the production environment. So traditionally, backgrounds were inferred, or lower chain backgrounds were inferred by direct measurements of the uranium and thorium with mass spectroscopy, and then you infer the progeny from that. However, you can see from the decay chain, most of the things after uranium and some higher up have relatively short half-lives, apart from lead-210. So what this means is that if you have radon-222 mixing into your copper during production and then decaying, you can have a broken equilibrium at this point where you have a high half-life. And so the activity you may infer from the uranium measurement may not give you the right amount for the lead-210. So a recent, in the last few years, development is being able to measure the alpha particle from polonium-210 directly, which sits here in the chain. And then this is used to infer the lead-210. And so this is a paper here by the Xmas collaboration where they use this XIA ultra-low 1800 detector to do this. In collaboration with them, we had a sample of our copper analyzed, and we found that in our copper we have roughly 29 millibecquerels per kilogram of this lead-210. So this is the dominant background source in our experiment. One way we could mitigate that, though, is through another interesting property of copper, is that it has a very high reduction potential. And what this means is that if you have copper ions in a solution with other nuisance ions like uranium or potassium or something like this, in an they will preferentially deposit at a surface. So what we did is we deposited an ultra pure layer of copper via electroplating onto the inner surface of our detector. So this is a cartoon of the setup. So we have our detector hemisphere here. We have some electrolyte containing copper ions, and then some other electrode here for putting a voltage across. And what we do is we put a particular voltage between these and drive a current, and this drives copper ions from solution onto the surface of our detector. So we could build up a layer of ultra pure copper to act as an inner shield to the detector to shield us from the decays of the lower uranium chain. And from a 500 micron ultra pure inner layer, we estimate we reduce the background rate below 1 kV in our detector by approximately 70%. It's estimated from simulation. So this was actually the setup of doing the electroplating. You can see here this is our detector hemisphere. And this was as a function of time, the thickness we plated, which is roughly corresponds to a rate of 1 millimeter per month. Following this, a sample of our copper was taken and assayed with a mass spectroscopy, and it's compatible with previous electroformed copper samples, which it was encouraging. And we've prepared a paper for submission to NIM, which should be coming very shortly on this. Okay, so after constructing the detector, we installed it again in LSM, where we could do a commissioning run. So this allowed us to test things like installing the sensor in a glove box. So here we're installing the sensor onto the rod, which goes inside the sphere. And then to access the inside of the sphere, which should not come in contact with air and radon, we have this glove box, which is flushed with nitrogen, which we use to lower in the sensor. So we're able to carry out these things on the detector. The other thing we were allowed to test was the assembly of the shielding. So this is the detector sat inside half of its lead shielding. And then when it was installed into the shielding, we were able to take some first data in LSM to test our acquisition and calibration system. The calibration system I'll discuss a bit more later. But we took some calibration data also with Argon 37, which we're currently looking at. And we're also able to test, I'll discuss more, but a new sensor technology. And the current status, so after being in LSM, we boxed up the detector and shipped it across the sea, and it's now in SNOLAB. So this was it arriving underground just before Christmas now, I suppose. This is the seismic platform next to DEEP, where our detector and shielding will sit. And this is the detector wrapped up ready to be installed in the shielding. And this is our high density polyethylene shielding assembled on the surface, which I think is now underground. So we're beginning to put the pieces together underground for our detector. So now I just want to talk about some of the recent developments in the detector technology, which will allow us to improve on our previous result with the spherical porous counter and dark matter search. So one of these is the multi-anode sensor, which I touched on before. So there's a small limitation, or a limitation with a single anode sensor, in that the electric field at high radius is coupled with our gain. So the avalanche gain is determined by the size of the anode and the high voltage, but this also determines the field at high radius. So there's some playoff to be made there. However, with this sensor, we get around that. So we decouple the gain and the high radius electric field by having multiple small anodes equidistant from some central point. So these small anodes mean that the gain is still determined by the size of the anode and the high voltage. However, at large radius, the electric field is determined by the collective electric field of all of these anodes together. And you can see, if you compare the red line, which is a single anode sensor, to the blue line, which is an 11-ball sensor like this one, 11-ball Equinus, there's a factor of 9 improvement in the electric field at high radius. So we've made some recent developments in this. So we're really pushing for high precision design and reproducibility. So we've adopted 3D printing techniques to produce this central electrode, which we then deposit on the surface a diamond-like carbon layer, which allows us to produce an electrode we can ground or apply a voltage to. So there's a publication coming, which is under review currently on these developments. Another thing we're working on is smaller anodes, and which will allow us to have higher gain, or even more anodes, instead of 11, having higher number of anodes, which will allow us to have a higher electric field at larger radius. And also we're working on precision assembly tools like you see here. This is one we use for assembling the Equinus. And in the future, we'd like to also investigate how we can read out individual anodes instead of reading out these collectively, or in the bottom half and the top half, reading out individual anodes. And this will give us some information about the location of ionization in our detector. Another crucial aspect is gas purification. So oxygen and water, or oxygen electronegative molecules, can lead to electron attachment in our detector. And this is a particular problem as the detector grows in size, because we have weaker electric fields at the outside. And so we may lose some of our primary electrons. So we need to filter our gas before we put it in the detector. Classic way of doing this is with a getter. However, these emanate radon. So in series with our getter, we're using radon traps. However, we found that radon traps remove methane, which is one of the critical gases that we use. So if we have a mixture of gas, it may remove some of that, which is not favorable. So we're investigating ways of filtering at both stages, as well as online gas monitoring in a recirculation system. So with like a residual gas analyzer to monitor the quality of our gas during a run. Up to this point, we've been operating in sealed mode, which has also worked well. So tests are ongoing for these developments. Another a key development with this detector compared to the last is the use of a laser calibration system. So we have a laser, I see in the cartoon here, there's the detector. We have a laser a fiber optic going into the detector, which allows laser light to hit the surface of the detector. Thank you. And extract electrons down to a single electron level. And with a second signal from the photodetector from the laser, we're able to get gas property information. So things like parameterizing drift times or even W value for the detector. And this will be running constantly throughout our data taking. So this allows us to also gain monitor. So here is the laser induced peak in our detector. Here is the peak from the argon 37 2.8 keV peak through the course of detection. You see there's some time dependent variation in the gain and the amplitude of the recorded pulse here, which is probably due to temperature variations. However, with this laser induced peak, we're able to correct for that. So this is a powerful tool we have now. Another powerful tool which we're developing is a complete simulation of the sphere, so a dedicated simulation framework which combines SHARP4 and Garfield++ along with finite element method calculations. So just as a quick example here, again, is the Akinos sensor. We read it out as a 2-channel, so we read the bottom 5 balls of the 11 here and the top 6 as 1. So we can simulate this or calculate this in a finite element method to find the electric field. We can feed that into our simulation framework in here, the weighting fields. And then the simulation framework will take us right from the primary interaction of a particle all the way through to the electronics chain, and the final signal would read out. So here you can see the signal generated on the 6 versus the 5 anode. So this is a tool we've developed, and this will allow us to also look at things like comparing to calibration data and also fiducialization of the detector. And all of these things come together for our new detector to produce this sensitivity projection, which I show here, which is for neon CH4 10% in this detector with an exposure of 20 kilogram days. And you can see that we're vastly improved compared to our previous detector. Okay, just in the last 10 seconds, just to say there's also a future for this. So I said that the majority of our background comes from the copper itself. So an obvious way forward is then to completely electroform the detector. So we have already funding to produce a fully electroformed detector underground, so we minimize cosmogenic activation at that point. And the current status is the R&D is underway for a prototype, a 30 centimeter prototype at the PNNL in the USA, and then the full scale 140 centimeter underground electroform detector will begin late next year. Okay, so as I'm out of time, I won't read through the summary slide. I'll just leave it there. Thank you.
Thank you very much also for being understanding of the time. We have a few minutes for questions now.
I might have one, if I can. So please. How the how the limits change when you use the electroform copper?
So I don't know if I have the numbers in my backup. Well, I can just say, so that, like I say, the majority of our background comes from the copper. If I remember, our background projection is something like 1.6 DRU. And the majority of this comes from the copper. So I don't have the limit here to show what we'd gain from that. But, you know, it's a, let me check if I've got the table. Oh, no, sorry, I don't have the table here, but
okay.
Yeah.
And in the limit, the pink is related to 2 different materials, right?
Yeah, so this comes from the hydrogen, this comes from the neon.
Yeah, because, okay, great. And have you performed so you show the path shape discrimination with the sphere or 30 centimeter. Have you done the same study with the 60 centimeter at Modan?
I'm not sure if we've done
it. The performance is the same. Like,
yeah, I don't know if we've done it with Modan, but we've done it with a 140 centimeter repurposed cavity on the surface, and we can see the same picture.
Okay. Thank you.
I have a couple of questions as well, unless there's hands there. But I don't see any hands at the moment. So the first question is if you have any plans to look for other kinds of signals in the same similar mass range, or this is something that you'll think about later?
Right, so I think this is something that's being looked at. I know that also one of the collaborators is looking at, say, a different type of dark matter. So he's looking for Kaluza-Klein axions and sensitivity to that. But yeah, I think we're looking into other, instead of the traditional nuclear recall, into other possibilities as well.
But you don't plan to make any modifications to your detector to optimize with respect to that?
Not for this detector, as far as I'm aware, but this is something we could look at for future detectors.
Okay, thanks. And then the second question is, how do you plan to treat the neutrino background once you get to 20? Is it maybe a bit early, but...
Sorry, when you mean when we approach?
When you approach the neutrino background levels, I mean the neutrino floor. This is something that is very far future, I guess. But
yeah, so this would be very far in the future, yeah. So, but for for two detectors down the line, one could think, then you'd need maybe, because in this region, the majority of the neutrino floor, I suppose, comes from the solar neutrinos. So you'd need some kind of directionality, which we could get through the Akinos sensor.
Okay. All right. Thank you very much, and thanks for the talk. Virtual round of applause as well. And, move on to the next one.
Yeah. So we can move ahead with the next talk. Adriano Di Giovanni, if you would like to start sharing.
Yes.
Thanks. And he will lead a discussion about Darwin experiment, the ultimate detector for direct dark matter search. Thank you.
Okay.
Yes, we can see the
slide. Okay, yes. Thank you very much. Thank you all for attending this presentation. Actually, I'm going to talk about the Darwin Observatory on behalf of the Darwin collaboration. So Darwin is mainly a dark matter detector. It's basically the last hope we have to detect dark matter with a non-directional detector in the mass range between 10-ish GeV up to 1 TeV. It can also cover a quite diverse science program, but more than that, is a very challenging enterprise. Because if we put together Darwin, then we'll be dealing with the largest liquid xenon targets ever built on Earth. And so we're talking about 50 tons of xenon. Then we need to also deal with the level of cleanliness that we require in order to operate the detector. And last but not least, we need to carefully plan a strategy for buying the xenon, because we are talking about the yearly worldwide production of xenon. So you need to plan over the time the acquisition of the xenon. So Darwin is one of the experiments that will be exploiting the effects of a Wimp interaction with the nucleus of a target, namely by using the light and the charge channel. So I'm sure that you already seen this slide many times. So the idea is to use these two information to build a discrimination procedure in order to discriminate the two families, the electron recoil family, in which we expect to see the background, and the nuclear recoil induced event family, in which we expect to see the dark matter interaction. The procedure is quite standard. So Darwin is a large TPC. So the idea is that you have a WIMP that interact with the nucleus of the target. Then you get a prompt scintillation that we call S1. At the same time, you have electrons that can be drifted up by means of an electric field that is active in the TPC. And once you get the gas phase, you get a second signal that we call delayed scintillation. It's actually an electroluminescence process that is proportional to the charge. So by playing with S1 and S2, you built your, let's say, rejection algorithm and you do some very, very nice path shape discrimination, but also you can actually record the positioning in X, Y of the event. And you can also get the information of the depth by measuring the arrival time distance between this S1 signal and the S2 signal. So you get information about the position, about the kind of particle that you are dealing with. So this comes from the Xenon collaboration, and as you can see, we have two defined separate families of events in the space of S1 and S2 in photoelectron units. Darwin will naturally follow the Xenon legacy. This project is now leading the dark matter search in these parameters since many years now, and the Xenon collaboration is actually commissioning the last and the biggest detector ever, the Xenon Anton, and the collaboration will start taking data very, very, very soon. So we have a benchmark, and if we want to do better than the benchmark, we need to be bigger, and we need to be cleaner, and we need to take care of a lot of things. So the TPC is huge. So the diameter is 2.6 meters, and so the drift length. So we will need a neutron muon veto, and of course we need to carefully choose the materials that we want to use to build the cryostat and the detector itself. So about the time scale, we are expected to start taking data sometime in 2027, so 7 years from now. That looks like tomorrow. And the project structure is quite common. The scientific community consists of 160 scientists from 29 institutions and 12 countries. We already have in place active working groups that are actually studying options and solutions for the construction of the detector and for the physics of the detector. And I have the privilege and the burden of being the convener of working group number 5, so the working group that deals with the light charge sensor readout for Darwin. So I don't have time to go through all the R&D activities of each working group. So the easiest for me is just to give you the sense of what we are doing in our working group. So as the entire world is doing, so we are also extensively studying silicon photomultipliers and see whether these devices are a good option to replace our benchmark, that is of course the PMT that Xenon is using for the Xenon Anton. So several groups are working on silicon photomultipliers, and but all of this, I mean, to my understanding, we are not yet ready to use silicon photomultipliers for dark matter experiments, at least liquid xenon based. There are also like a spin-off of silicon photomultipliers. So there is a group working in digital and developing digital CPM, and this is very preliminary. I mean, the left side of the slide. So in Heidelberg, they are testing the capability of being able to switch off the noisiest pixel of silicon photomultiplier. So basically, in this plot, you see that by switching off 5% of the pixel, meaning that your photodetection efficiency becomes 5% less. So you lose 5% in terms of photodetection efficiency, but then you gain something like a factor 1000 in terms of dark counting rate, that at the moment is the killer for this application. We also have an effort in trying to build a suitable electronics for heterogenic environment with the idea of merging together, of coupling together many channels and operated them as a single channel. We are also looking at hybrid detectors. So for example, on the left, you have the vacuum silicon photomultiplier tubes developed by INFN Naples. And the idea here is that you combine the best quality of PMT, so the sites basically, with the fantastic and distinctive single photo detection resolution of a silicon photomultipliers. On the right, we have a balone that's again a quite, it's not super new, but now I think it's actually, this technology is improving a lot. And this will offer a huge sensitive, a huge coverage for your targets. And the readout will be done by using a scintillating layer that will convert the electron into a flash of light and a silicon photomultiplier. So we are considering several options for assembling the detection array of Darwin, but at the moment I think the PMT is the best candidate. Darwin again is a dark matter detector, so we look for very rare events, and when you look for very rare events, your fight is against the background. So we actually, what I'm showing now, it's a simulation, but it's a simulation with the lesson we learned from all the former experiments like xenon, like LZ, like all the other experiments that are dealing with liquid xenon. So we try to identify the main source of the nuclear recoil background and the electron recoil induced background. So as you can see on this chart, on this pie chart, the main contribution comes from the cryostat, even though we are selecting titanium as one of the cleanest titanium that you can find on the market, from the Teflon, and of course from the PMT. To me, the only reason to replace the PMT is because the radioactivity. What is the goal of our job is actually to run a detector in which background is neutrino induced event dominated. So we want to keep under control the main sources of background, so the intrinsic background, namely what is inside the xenon, and the material. For example, in this plot, you see that we are actually considering a quite low concentration of krypton and of radon, because we think, at least looking at what xenon is doing, that this kind of parameters can be kept under control. And then there is a nice story about the xenon 136. So the xenon target, it's actually a mixture of 9 isotopes, and the xenon 136 is a bit annoying because it's a double beta emitter. So in principle, you can actually ask for a depleted target, but then you lose the power of doing some neutrinoless double beta decay search. So it's matter of trade-off. So considering this contribution, if we are happy with this contribution, then the electron recoil background will be dominated by the neutrinos from the PP chain from the beryllium-7. Of course, we'll be very much sensitive to solar neutrinos. The coherent neutrino nucleus scattering is, as you know, a killer for this kind of detectors, but we'll be also able to see neutrinos from the helium proton chain, from the diffuse supernova background, and also atmospheric neutrino, even though all these contributions are quite suppressed by the solar neutrino interaction. So if we put together all these ingredients, we can see that Darwin will be filling the void left between the present and the next future experiments and the neutrino floor. Then another nice feature of xenon. So as I said, we have 9 isotopes inside the target, and 2 of them actually are non-zero, have non-zero spin. And so if you have something that have non-zero spin, you can actually test spin-dependent models for dark matter. So in these two plots, the one on the left is mainly for protons, the other on the right is for neutrons, actually report the predicted limit for Darwin, assuming an exposure of 200 tons per year. So xenon and ton is missing, but the curve will be somewhere in between xenon 1 ton and Darwin. Will be also sensitive to solar action and action-like particles. So these plots actually comes from a quite old paper that we are trying to update these days. And in order to put in context the last results from the xenon 1 ton, this plot is very preliminary, so it shouldn't be here, but just to give you the idea of where we are. So xenon 1 ton, the measurement is about here, while Darwin will be here. Yes. So what happens if we fail? So what happens if the dark matter is hiding behind the neutrino floor? So we still have something to do because, as I said, the xenon 136 can be used to test neutrinoless double beta decay. Again, in order to run this analysis, you need to carefully know the background of your detector. And again, the cryostat, the Teflon, and the PMT are the main contribution to the background for this kind of analysis. So what you can do, you can just do some fiducialization of your volume, and then you realize that if you take in account 5-ton fiducialization, then the number of spurious events becomes small. 5 ton, it's not a magic number, but it's when the material-induced background equals the intrinsic background. Again, in this analysis, we are considering a very low level of radon-222 contamination, so at the level of 0.1 microbecquerel per kilogram of xenon. And of course, we cannot use a depleted target, otherwise we lose our capability of doing the neutrinos double beta decay. And as you can see here, there is a quite annoying contribution, namely the xenon 137. That xenon 137, it's not occurring naturally. So it's actually something that is produced when a muon interacts with the rock or with the shielding of your experiment, produce a neutron. The neutron is then absorbed by the xenon 136, and then you have a beta decay. And so this electron will mess up with your detector, and this will simply add a continuous spectrum in the background that is quite annoying. But then you also have the cesium 137, but the the decay time is very long, so you don't care about the decay of the cesium 137. That said, so the presence of the xenon 137 strongly depends on the neutrino flux. So in principle, you have two angles to mitigate this effect. Either you go deeper underground, so the muon flux is actually reduced, or you build the dream of every physicist, so the famous 4-pi veto, in which you tag all the muons, not only the muon that eats your muon veto, the water tank of your detector, but all the muons, because you are actually sensitive to the neutrons that can be produced by the muon interaction. So we did this exercise of considering the Darwin baseline, meaning that the Darwin baseline contains all the background model is the one that I was talking about a few slides ago, plus its installation at Gran Sasso National Laboratory. So we studied the background in the region of interest in which we expect to see some neutrinoless double beta decay, and then we did the exercise of adding a 0.5 counts per year signal. So you will see a small excess in the plot that will pinpoint to the possible neutrinoless double beta decay. Of course, this can be improved by going deep underground or improving the cleanliness of your detector, and then you start being competitive with other dedicated experiments. Of course, we'll be also sensitive to solar neutrinos via electron scattering. So if we focus, for example, the neutrino of proton-proton chain, that is this curve in this plot. So in this plot, we have all the components, so backgrounds and also neutrino from other processes happening in the sun. And if you zoom this plot, you see that the PP neutrinos are already above the background, that again is mainly driven by the xenon 137. This analysis would really profit of having depleted targets, but again, this is done for considering natural targets. So if we run the experiment, then we could actually say something about the survival probability of the electron neutrino in an energy region that should be the lowest ever tested. And also we can actually say something about the mixing angle and as a function of the exposure and natural or depleted targets. Last but not least, again, so the CNS neutrino is a killer background for dark matter search, but we can actually will be able to measure it and as well as neutrinos from supernova. So in this paper of a collaborator of us, we actually demonstrated that we'll get 5 sigma significance up to 65 kiloparsec distant supernova explosion. Again, so I think time is a concern, so I'll leave you with the conclusion of my talk. Thank you very much.
Thank you very much, Adriano. Are there any questions? Bjorn. Please.
Sorry, can you hear me now?
Yes.
Okay.
Now.
Sorry, I was double muted. Yeah, I have a question about the backgrounds. You showed the simulation where you have 30% PTFE, 30% PMTs. Are these based on which steps are you assuming you're in Gran Sasso?
Yes, so the baseline is in Gran Sasso, and actually we are using, I would say, the database of the screened material of former experiment like Xenon, like LZ. For the PMT, is the baseline is the PMT of Xenon 1 ton.
So given that you have so much PTFE and so much background, is this mostly neutron-induced backgrounds from the fluor, or what are the backgrounds, or outgassing?
So the problem PTFE it can be either. So I didn't run this simulation, but I think it's actually so the ingredients are both, so outgassing and also the surface contamination of PTFE. That is a known problem.
Okay, is it possible to replace with Tyvek in the TPC or not?
Sorry, say again?
Can we replace this with Tyvek in the TPC or not?
I would say yes. So again, so the project is yet to be created. I mean, we have already, everything in place. So there is a letter of intent, but the detector is not yet there. So I think we have time to work out this, let's say, to deal with this large contribution of background. In principle, I think so.
Thank you.
So we might have time for another quick question. If not, we will move to the next speaker. Okay, so let's move ahead. Thank you again, Adriano.
Thank you, my pleasure. So stop sharing.
All right, so if the next speaker, Paolo, wants to share.
Yep. Oh, sorry.
Oh, the camera is good.
Let me share. Okay, can you see the slides?
Yes, so first, thank you.
Thank you. Hi, everybody. Yeah, so I'm going to report about the latest results from the DarkSide 50 experiment at Gran Sasso. DarkSide 50 is a liquid argon experiment searching for WIMPs. And the detector design is a basically is a dual phase TPC. We've seen also in the previous talk as how these detector configuration is ideal in order to address some of the challenges for this kind of searches. And here I'm talking about the scalability of the target, the ionization and scintillation yields, which enables to have relatively low thresholds, how such a detector allows for 3D vertex reconstruction, which can be exploited in order to reject surface events or multi-sited ones, as well as how they allow for particle identification in order to reject backgrounds. So a quick recap of the working principle of a dual phase TPC. Whatever interacts in the bulk of the target produces both prompt scintillation, which is detected by rays of photodetectors, as well as ionization charges, which are drifted upwards up to a gaseous region where they are extracted and accelerated. And there they produce a secondary light emission, which is proportional to the number of charges. So the time difference between the two scintillation pulses provides the vertical coordinate of the event, while the light pattern on the top array of PMTs provides the localization in the XY plane. So as I said, DarkSide 50 is a dual phase TPC, which is operated since 2013 at Gran Sasso. It is filled with a relatively small target, 50 kilograms of argon, which is extracted from underground. And I will come back on this later. The core of the detector, the TPC, is installed inside a 30-ton liquid scintillator Vita, which provides basically 4-pi detection for radiogenic neutrons. And the whole system is placed in turn inside a 1 kiloton water Cherenkov detector for muons. The S1 and S2 yields of the TPC are in the order of 7 photoelectrons per kV with the field on for S1 and 23 photoelectrons per extracted electron for S2. The electron lifetime is quite good, actually much larger compared to the maximum drift time of electrons in the vertical direction, which is limited by the small size of the TPC. It's only 36 centimeters. So one of the main aspect of DarkSide 50, of course, is the use of liquid argon, which is, sorry about that, which allows for rejection of electron recoil background thanks to the so-called pi-shape discrimination. This technique is based on the different time characteristics of the scintillation pulse, the S1 signal, which is different for nuclear recoils, which is the typical signature respected for WIMPs and also neutron, and beta and gamma backgrounds. So if one plot the fraction of the S1 signal in the first 10 tens of nanosecond of the signal itself, here in this plot on the top left, is shown as a function of the S1 signal itself, which scales with the energy. One can see and one can separate pretty neatly the two populations of nuclear recoils at the top of the detector from the one of electron recoils at the bottom. At nuclear recoil energies of the order of about a few tenths of keV. So this, of course, guarantees a separation and a background rejection of the order of 10 to the 9. We have a talk after the break from the deep collaboration, which will discuss this more in detail. The second feature of DAXI 50, which contributes to the background mitigation, is the ability to actively reject neutrons and gammas, actually. We can do that by tagging events where a particle is interacted multiple times inside the target. And this will show up as an event with multiple S2 signals. And in particular for neutrons, the presence of this 4-pi liquid scintillator veto around the main target can be used in order to tag events where a neutron has interacted only once in the sensitive target and then has left the TPC, but has been captured in the veto, depositing energy there. So the veto is constructed such as a very high neutron capture cross-section probability thanks to the loading with the natural boron. And this means that looking at the coincidence between TPC and veto, one can tag this sort of events. The third feature of DAXI 50 in terms of background mitigation is the use of argon extracted from underground. The reason is that atmospheric argon is pretty radioactive at the level of about 1 becquerel per kilo due to cosmogenic activation in the atmosphere. And this is a limiting factor in the size of dual phase DPCs, which cannot exceed the ton scale, as otherwise would be limited by pile-up if using an atmospheric argon. So the solution, and then demonstrated by DAXI 50, is to extract argon from underground sources, which has been shielded from cosmic rays during thousands of years, and thus it is depleted from argon-39 that decays away with a half-life of 270 years. So the DAXI 50 was filled with an underground argon field in 2015, and one can see here the comparison between the spectrum acquired with the atmospheric argon in blue and the underground argon in red. The result of a multivariate fit, which I'm going to mention also later, reports depletion which is larger than a factor of 1,000, enabling the future of the liquid argon program, which was also mentioned in one talk yesterday, the DAXI 20K. The other thing that I want to mention is the fact that this fit result reported the presence of some unexpected krypton-85 component, which may reveal an infiltration of air, meaning that the actual content of 39 argon is maybe even smaller than what reported here. Okay, so these three features that I described on that side were all fundamental for the physics results of the experiment. The first one that I want to mention is the high mass WIMP analysis, which was performed with actually a blind analysis published in 2018. So the idea was to blind and to apply this blinding mask on the data sets that we collected of more than 500 days. This is once again the pulse shape discrimination parameter versus the S1 signal. And we expect nuclear recoil underneath this blinding mask while electron recoils are here. So the idea is to is to identify the boundaries of a WIMP search region in which we minimize the background and we set a limit of 0.1 events in the full exposure while maximizing the acceptance to nuclear recoils. So we have, in order to train our selection criteria and the boundaries of the WIMP ROI, we have access to calibration data and to a preliminary 70 days data set collected at the beginning of the data taking. So this table on the bottom represents the background budget for the full exposure before the box was open. It includes degraded alphas that can leak into the WIMP search region from the high energy side. It includes cosmogenic and radiogenic neutrons, which have been extensively modeled and simulated, and especially electron recoils, which may leak from the electron recoil band to the nuclear recoil one. So what I'm going to show here is a quick animation where you can see the boundaries of the WIMP search region and the cut flow and the effect of each of the cuts in order that were applied in order to clean the data set. This is the result after the last cut based on TPC variables is applied. So we have still 2 events in the WIMP search region, but those disappear when we look at the coincidence with the veto, leaving us with no events in the WIMP search region and a background-free exposure of more than 500 days. This is the acceptance, the cumulative acceptance of the various cuts. So these results demonstrated the potential of liquid argon to perform background-free searches. The extracted 90% confidence limit is not, sorry about that, is not really competitive with xenon-based searches due to the small mass, but is shown in this plot with the red line. I'm also showing, once again, that the deep 3600 exclusion, which will be discussed later, and the xenon results, which are much stronger. Of course, the plan for the next generations of both xenon and liquid argon is to fill this gap and to reach the neutrino floor in the next decade or so. The second item that I want to discuss are the results in the low energy side of the spectrum, which demands a totally different approach, especially below 3 kV electron equivalent recoil energy. In fact, we cannot access the scintillation signal because the probability for it to trigger the detector is very small. So we need to rely on the ionization only signal. This means that we lose the fiducialization, at least in the vertical direction. Of course, there is no S1, and there is no discrimination of electron recoil background. However, we can benefit from the multiplication in the gas, as I mentioned earlier, a factor of 20 or so, which enables very low threshold and a trigger efficiency, which is basically 100% even for events, for ionization events, which produce only a couple of ionization electrons. So this trigger efficiency is estimated with a full optical Monte Carlo, which is based on our understanding, our model of the S2 signal, which is fitted from a sample of high energy. And by the way, it plateaus here at about 0.42 because we're still able to fiducialize in the radial direction based on the light pattern on the top array of photodetectors. We need a calibration in this energy range, and this is done thanks to the presence of argon-37, which was not actually planned. We found argon-37, whose origin is probably cosmogenic activation during the shipment of underground argon to Gran Sasso. It decays away in a few months, but at the beginning of the data taking, it shows up with these 2 nice peaks centered around 2.8 kV and extending down to 270 EVs. Below 270 EV, of course, we need to extrapolate to calibrate the lower energy part. So the energy scale is combined with a background model derived for the high mass WIMP search in order to derive the background model for the low energy side. For the high mass background model, we relied on full simulations of each radioactive component, namely decay chains and the major contaminants, including the internals, argon-39 and krypton, in all the detector materials. We applied a multivariate fit, which exploits not only the energy of the reconstructed event, but also the position. So we extrapolate this down to low energy. And I remind you that we are talking about, this model is covering really a wide energy range, while the searches are concentrated only in the first few bins of this plot. The next step is the calibration of nuclear recoils down to the keV energy scale and below. Compared to electron recoils, of course, we need to consider also the quenching due to nuclear collisions, which adds 1 degree of freedom. In order to do so, we fit an effective model, which takes into account both the quenching and the recombination probability, to data from neutron sources. Those neutron sources are dipped into the detector. They're placed close to the cryostat. And we have 2 of them, americium carbon and americium beryllium. The fits are shown here on the right plots. And we're also using data from external experiments, which are typically done with neutron sources at fixed energy, in order to further constrain our fit. And this is the resulting ionization yield as a function of the recoil energy. As you can see that the systematic error is pretty large. This is the final data set in the energy range, which spans from 0 to roughly 3 keV electron recoil equivalent. The data is shown here, and the fit with Monte Carlo components are the colored lines here. We have, of course, a dominant contribution at very low energy, which is not modeled. This is why we set a minimum threshold for the analysis at about 4 reconstructed electrons. Superimposed, there are also expected spectra, PDFs for low mass WIMPs from roughly 2 to 10 JV. And this analysis allowed us to set very stringent limits on the WIMP nucleon cross-section, which at the time were leading between 2 and 6 JV WIMP masses. Now, the xenon experiments, Xenon 1 ton provided slightly stronger limits in this range. And also, we have published an interpretation of this result also in the terms for what concern the WIMP electron coupling. Those results are shown on the right. So can we do better? And yes, in the past year, we have been working on improving these results. First of all, we have a larger statistics, almost a factor of 2. The 2018 dataset. We've been working hard in order to improve the data selection, in order to both recover acceptance for certain classes of events, which were wrongly neglected in the first analysis, and also to improve the rejection of pathological or unmodeled ones. As an example, for these 2 categories, I'm showing here at the top, a typical S1 plus S2 events where the time difference between the 2 corresponds to the maximum drift. In this case, this is an event located at the bottom of the TPC. We have S1, and the ionization energy, or the energy of the event, is reconstructed using the second pulse correctly. There are, however, cases where the topology of the event is such that the S2 signal is the one that triggers the detector because S1 is very small, and we were wrongly reconstructing the energy of the event using the second pulse, which is instead a photoionization signal produced by the scintillation of the in the gas. So we are recovering acceptance for these classes of events, which were inducing a slight bias in the data spectrum, as well as for events where S1 and S2 are in pile-up, as shown in the middle schematics. We're also improving the background modeling. The first item that I want to mention is that we are extending it above 50 electrons. This means that we can constrain better the background above a region where we don't expect any more signal. If I remember, 10 GeV WIMPs only produces signals up to 80 electrons or so. And we also have more accurate PDFs. For example, we separated the terminal contribution of argon-39 from krypton 85. We also have improved calibration, both for the nuclear recoil energy scale and for the electron recoil ones. And these allow us to disentangle, for example, detector effects from the intrinsic fluctuations of the signal and the energy scale. One can see, for example, here on the bottom plot, this is the equivalent of the electron recoil calibration with argon-37. We are now able to reproduce all the features of the signal, which are induced by detector non-uniformities and which were firstly averaged out. So the overall effect of this is a reduction of the systematic uncertainty. And this improvement in the modeling of the signal, together with the larger statistics and an improved calibration, will bring a significant improvement in the exclusion limit for light WIMP nucleon, for light WIMP masses. So unfortunately, I am unable to show any preliminary result because they are still being finalized, but we expect significant improvement. As before, the same data can be used to constrain other sort of interactions with electron final states or, for example, actions. Something else that we are working on is the implementation of the Migdal effect that was already mentioned in a talk yesterday. And it may significantly enhance the sensitivity to low mass WIMPs. So what we're working on at the moment is an implementation where we conserve the correlation between the nuclear recoil energy and the electron recoil energy. And we plan to produce PDFs for the signal which take care, which account for both the effects considered as independent. This work is done in collaboration with theorists, and it will also be finalized very soon. My last slide is on a result which is indeed instead finalized and published, is an interpretation of the IMAS WIMP null result in the framework of effective field theories. What we show here is that, well, we are used to compare exclusion limits from different targets in the framework of the standard scalar interaction, but there are 15 operators that may describe the WIMP nucleon interaction. And if one consider, and one can interpret exclusion limits assuming a different kind of interactions. This is what is shown here. And for more details, you have to refer to this. I suggest you to open this publication. It shows how there are important variations up to a factor 100, only for considering our case of argon-39. And this, of course, points in the direction of highlighting the importance of complementarity, especially in the case of a positive observation, in order to probe the full parameter space. So I think I am out of time, so I will leave the conclusion here, and thank you so much.
Thank you very much. So we have time for a couple of questions, and then as highlighted in the slides, many of the speakers have Zoom discussion rooms that are open after the session closes. You can find them on the agenda as well. So is there any questions from the audience? If not, I will ask one. So I'm curious about the statistical analysis that you're using for setting the limits. So do you do a invariant likelihood with the signal hypothesis in the background, or is it something different?
Yes, I assume you're referring to the low mass WIMP search, and this is exactly the case. So we have background predictions that are constrained both in shape and in rate. and we test our signal hypothesis. We have a couple of systematics which are included, namely on the scaling of the backgrounds and on the energy scale calibration, which are represented by the bands which are shown here. So this is, for example, for nuclear coils. So one of the reasons why we expect a big improvement is that we improved this calibration by a significant amount, and we reduced the systematics on the nuclear coil calibration.
And do you have like how much in this plot, in this kind of projection, how much does reducing a systematic gain you?
I cannot answer in the sense that I don't know what is the effect of simply reducing the systematics.
Again, I don't know if you have run the with and without the systematic, but this is just a curiosity.
I will have to check. It's not trivial to.
Yeah, no worries. There's probably time for one more question if anyone has it. If not, virtual applause again. Thank you very much.
Thank you.
And we can move to the next speaker.
Which is coffee break, I guess.
Right, I forgot. Coffee break, right. So yes, so the next session will restart. Let me just check on the agenda. So we're starting 15 minutes then.
If Noah is online, would you mind start testing sharing?
I can't do that until the, okay, there we go.
Okay, yes, sorry.
Okay, sorry, I'm.
No, that's okay.
Does that look correct?
Perfect. Yes, try the second slide just to make sure that, yeah, great. And would you mind to have then your video on when you?
Oh yeah.
Just when you talk.
Just make sure it looks okay.
Oh, that's great.
Oh, do you get the net? Yeah, actually, how do I see myself now?
Okay, so if it's disturbing, then turn it off. I don't know how.
No, I can't even see myself. So as long as I'm like in frame and.
Yeah, you're great.
Okay.
And if maybe we still have 2 minutes, if Sergio is there. I know that Simone already tried the sharing. So if Sergio, I don't see him anymore. So I hope you will connect later. Okay. So 1 minute left before restarting the session. Okay, so it's noon 30 Eastern. So I think we can resume the session, and I will restart the recording. So we will start the last session of this parallel of today. And the first speaker is Noah Kurinsky from Fermilab, and he will talk about super CMS searches for low mass particle dark matter. So Noah, I'll leave it to you.
All right, thanks, Sylvia. Yeah, so this is a fairly broad topic, and I included a bunch of archive links where possible. I posted my Zoom info at the end for detailed questions, because I'm going to be skipping through things fairly quickly. We've done a lot in the 2 years since the last ICHEP, but even in the last 3 months, we've published a lot of new dark matter results. So I'll talk very, very briefly about the technical challenges, because they've been covered many times in this session already, and then move to the results we published, and then talk a bit about what we're doing both in the next year as well as with Super CDMS Snow Lab. So as many people noted, right, this is the normal particle dark matter cross-section versus mass space you're used to seeing. And there's generically these low mass and high mass regions where in the high mass region, really you're limited by exposure, whereas most of the low mass experiments, exposure is important, but it's very threshold driven. And what I also wanted to highlight is, in the last few years, these regions are also broken down based on coupling probed. And so the low mass region below about 10 GeV and about 1 keV in recoil energy also happens to be the region in which kinematics of recoiling off of electrons is actually more favorable than recoiling off nucleons, and where you flip from preferring a heavier target to get more recoil energy from a given interaction to a lighter target to reduce the kinematic mismatch between your target and the dark matter. So this is just generic scaling, but in CDMS we use silicon and germanium. So silicon would be a slightly better reach at low mass, whereas germanium has a slightly higher reach at above 10 GeV. In this talk, we're only considering sub 10 GeV results. So, and I'm focusing on silicon results. The super CDMS detectors historically have read out both charge and phonons. And so the picture of a dark matter event is some scatter at the site shown in this crystal diagram at the right. It immediately produces phonons, lattice vibrations, as well as charges, and the charges are drifted in an electric field to be read out at the surface. Historically, we've used both phonon and charge sensors to read them out separately, and we apply a small field. But if you apply a large field, as shown by this equation here, you can actually get the total phonon energy just to be proportional to the number of electron hole pairs generated. And the first demonstration of this effect at the single electron level was done in 2017 by a group at Stanford. And so the plot on the bottom right shows this effect where if I look at no events, I get a Gaussian around 0. If I look at 30 photons, I get the distribution at around 50, 60 eV shown in the dashed line. And then as I increase the voltage, I start to see the single electron pair peak first at 50 volts and then at 150 volts. So we can use highly sensitive phonon detectors with resolutions below 10 eV, both as phonon calorimeters for dark matter searches, as well as charge sensors for dark matter searches. And so the Super CDMS collaboration has evolved over the last few years as we prepare for the ultimate, the SNOLAB experiment, into a bunch of different facilities. And we've developed sort of a flow of new technology going from surface R&D facilities, of which we have a few. Stanford, Northwestern, Berkeley, and Texas A&M are the sort of leading institutions on various efforts of R&D. And for dark matter results, really what's happened recently is we've got a bunch of results published from surface facilities. We've moved both of those detectors that I'm talking about today into the underground facilities. So Nexus has about 300 feet of overburden at Fermilab in a highly shielded low background fridge. And Qt is the same, actually the same cryogenic system, but it's underground at SNOLAB near the future site of the Snowbox. And so those are currently taking data, and I'll talk about prospects for that in a little bit. And then installation is in progress for the Snowbox, which will host the full Super CDMS SNOLAB experiment. So for electron recoil, that'll be the first topic. The flow has basically been through the surface facilities to Nexus. Nexus is set up with high voltage readout that is needed for those detectors, as well as the fiber, laser fiber calibration system I'll be talking about. And the idea there is lessons learned will feed forward to the high voltage style detectors run at SNOLAB. And for the nuclear recoil side of the searches, again, initial designs are tested in the surface R&D facilities. They're going to Qt, which is better set up for the ultra low background and some of the longer time scale nuclear recoil calibrations. We'll actually be running one of the Super CDMS towers in Qt before going to the full Snowbox. And so this is sort of the direction of the arrows is sort of increasing exposure and lowering of backgrounds. And the goal of the first runs is always understanding detector performance and lowering thresholds. So moving first to electron recoil searches, this is what we've been calling Super CDMS HVEV, are the detectors running right now. These are gram scale and resolve single charges. The long-term goal is to scale this up to the high voltage detectors at SNOLAB, which we've made some prototypes of, but due to the high backgrounds at the surface, we have not yet been able to operate them at the same level of sensitivity. And the main challenges here are charge leakage induced either by light backgrounds or high energy backgrounds, understanding the quantized backgrounds we see, and then maximizing charge collection efficiency and understanding position dependence in our backgrounds. So the first run, this was 2018. You can see the scale of this experiment is much smaller than most of the other experiments shown in this session. So it's a 1 gram crystal. This had a 10 EV resolution for the best run and was calibrated. You can see a fiber coming up at the back of this crystal. So the calibration was done by pulsing a red 1.9 EV laser and observing quantized peaks from the laser. And so this was the first device to demonstrate this effect, and also the first device to set a limit. So the spectrum that we published in 2018 looks like this. We could account for the first and second electron hole pair peaks just with detector physics, but we saw this somewhat non-quantized background extending out to all the way up to about 10 electron hole pairs, at which point it starts to become consistent with the Compton background. So the non-quantized nature of this, you can see the laser is fairly quantized, that's the black, but the background being non-quantized is very confusing. And so the goal coming out of this, after setting the dark matter limits, was to improve resolution and device understanding to quantize that background so we can start to actually model it. So the run 2 setup, so this was taking the run 1 detector, making some improvements to lower the threshold, and then improving the enclosure. And so the picture on the right shows, if you compare to this setup, this is fairly exposed to the fridge. This is actually in a light tight box, which is mounted inside of this fridge. We ran otherwise the same program, doing calibrations with this laser fiber and exploring different voltage biases. And the result is that we actually were able to quantize these backgrounds much more. This is a result that was put out in May and is undergoing final review in PRD. The really surprising result here was that improving the resolution, we quantized the backgrounds, and the rate of those quantized backgrounds was the same as run 1. So let me highlight, these are different detectors made by different facilities with different crystals running at different sites with different backgrounds. So the consistency between the run 1 and run 2 limits was actually pretty shocking. So we are convinced that at least above the 1 electron bin, these are real backgrounds, and we're working on understanding them right now. So that was a spectrum for the run 2. We set limits on electron recoil, dark matter with momentum dependent and independent form factors, as well as dark photon absorption. You can also see a fairly recent result here in the dark photon absorption and the ALP absorption from Super CDMS Sudan. This was a reanalysis of the full Sudan data set, and that does actually set the most competitive limits above 40 EV or so. We were the first collaboration to set these ALP limits, although that parameter space is largely excluded by astrophysical constraints, and you could expect the other dark photon limits to be cast into this space as well. So this is a recent result. If you want more details, I want to point you, Valentina Novati gave this great APS talk. This actually links to the video. So you can go there for more details, or you can come ask me questions on Zoom. So switching over to the low mass nuclear recoil searches, this is sort of where I want to highlight in this talk, because we actually have one result that hit the archive last night. That was not actually the plan. It was submitted a week and a half ago, but it just got held up until last night. So this is the first time this will be shown, and I anticipate questions. So I want to leave a little bit of time at the end to talk about this. For the nuclear recoil searches, we have sort of 3 technologies moving in parallel right now. The Super CDMS CPD is a cryogenic photon detector designed for coherent neutrino scattering and readout of neutrinoless double beta decay. So that's the result I'll present now. There's going to be the HVV detector, which looks for ERDM, run at 0 volts with the 3 EV resolution. So those are results that will be coming out by the end of the year. And then we're starting to run some of the prototype SNOLAB detectors at CUTE, which is the SNOLAB underground facility. And the major challenges here are maintaining these low thresholds and calibrating below 1 keV. So this nuclear recoil detector, it's bigger. It's about 10 grams. It's a 3-inch, a standard 3-inch silicon wafer, and it only has 1 readout channel. So the design driver here was large area, low resolution, and it also runs at a very low TC. So these are all cryogenic detectors. And this detector in particular was the lowest sensor transition temperature we have run to date for Super CDMS. And as I said before, it's designed originally for degraded alpha rejection, but to do that, it needs exquisite energy resolution. And so we did a lot of characterization on this sensor. We also, we did this iron 55 calibration, which I think is fairly standard now for these low mass searches, where you get a 5.9 and 6.4 keV calibration line. You can also see a silicon escape peak around, I think, 4.9 keV, and then there's an aluminum fluorescence at 1 keV, and that's the primary, these are the 4 primary points used to linearize the energy scale. And what you notice immediately about this low energy region is while there's a flat background, which is what you'd expect from Compton's, especially due to the fact that the source can't be turned off in this configuration, it does rise at low energy. And so we were able to achieve a threshold of 20 eV for the search. We do cover new mass space. It's the first nuclear recoil search to pass below 100 MeV in dark matter mass. And you can see, though, that the reach for that low threshold is pretty limited by this low energy rise. And so one of the, immediately this is A, both interesting, because it excludes new parameter space, and B, you can see that it sort of starts to outline a range of masses around 100 MeV where we're seeing an excess. And Yoni talked yesterday about other experiments, both these CREST experiments that also see excesses of low energy. So this starts to add more data in a very significant way to this, this idea that there's something new at low energy, whether it be a background or some interesting signal to probe. So this also, this detector is now being run at Qt as well. So we're hoping to add data with the same detector in a lower background environment to better understand the source of this low energy excess. Okay, so future prospects. I mentioned sort of as I'm going through this, how we move from the results we put out over the last 3 months to more sensitive science, longer exposures, running underground. And so from the picture I showed at the beginning, there's sort of 2 paths we're going down now. The electron recoil path is proceeding forward at Nexus, which is at Fermilab. This is right next to the Sensei setup as well. And so what we're working on right now is working with Sensei, who were able to reduce their backgrounds with extra shielding to better understand these low energy backgrounds in the electron recoil space and validate the observed behavior they saw, which is that as they add shielding, they start to see backgrounds going down. If we can get our backgrounds under control, this is supposed to be a 100 DRU facility, so we should be able to probe well below thermal relic density at Nexus with HVEV, assuming that the shielding works as designed, and we're in the process of building the shielding now. Qt, which is at SNOLAB, this is also fully functioning. It's running, taking data now with PD2, and it has this giant water tank. It has a lot of lead, so this is designed to be a 10-ish, sort of 10 DRU facility. Also in the process of understanding background they see and working out some kinks in electronics, but we expect science results from that within the next year. And then there's more results from Sudan data coming out. There's going to be Migdal/Bremsstrahlung limits within the next month or two. The paper is just working its way through collaboration review. There's a LipSearch paper also coming out very soon, and there's a bunch of solar neutrino science being led by our new analysis coordinator, Emmanuel Michelin at UBC, and David Sudano at Madrid. So one of the most interesting things I want to highlight and prime people to look out for by the end of the year is this follow-up of ER-NR comparison. So I showed earlier a spectrum of the ER spectrum for HVV run 2, where the background didn't change. And so the exposure for that run is shown on the top right. So the 100-volt limit is what I showed. That had by far the most exposure. But we also took data at different voltages, especially at 0 volts. So at 0 volt, this is just a fall-on calorimeter. And over the last 6 months or so, we've optimized the readout. What we actually did was record data continuously. And so we can go back and trigger. And we've re-optimized the trigger so that we get a threshold of about 9.2 eV for it. So that's about a 3 sigma trigger for this detector. It has a 3 eV resolution. And so, what we're in the process right now of modeling the noise contribution to the spectrum that passes through this trigger, because obviously, a 3 sigma trigger is not going to be noise free. But it will have a threshold that's lower than PD2, a slightly improved resolution. We should be able to compare that. And we should be able to compare the spectrum from this detector in the calorimeter mode with the electron recoil spectrum and figure out the source of those events, whether they're nuclear recoil or electron recoil, and help better probe how to reduce them, or whether they're starting to be some irreducible background. There's also plans for a larger payload at Nexus. We're going to scale that up to 10 grams within the next month or two. This is just a plug for Nexus. It's a multi-purpose underground user facility for low temperature science. So this shows the current HVEV payload, which is working really well down there. It's the same detector that was run in Run 2. There's this dilution fridge on a frame, and the lead shield is under construction right now. So it sits on this platform, and it's being stacked as I speak, and we'll have the first data on background reduction after shielding within the next couple of weeks. This facility also does, if you're interested in learning more about it, come talk to me. We're also wiring this up for MKID readout, SNSPDs, and some qubit studies. So it should be a very interesting underground facility for more general science. So finally, Super CDMS Snow Lab. So this is the ultimate in low threshold detectors. We have silicon and germanium, which are 600 gram and 1.2 kilogram detectors respectively. They have 12 channels, and they're expected to have resolutions on the order of 10 to 20 eV. One big thing we're working on right now is that large channel count makes event reconstruction much more complicated. They're very fast signals. They're highly localized. And so there's a group that's leading some machine learning-based reconstruction studies, which should both minimize resolution and help extract a fairly accurate position for events in the detector. We also have two types of detector. One is these HV style, and the other is the ICHEP, which is the older style of separate phonon and charge sensors. The HV should get to lower threshold than the ICHEP. The ICHEP will be better for validating backgrounds in the cryostat. The facility will be underground at Snow Lab. I'm sure many of you in the dark matter community are very familiar with Snow Lab. Our part of the drift is shown on the bottom right here. So Qt, which is what I've been talking about, that already exists. That's where it is in the drawing. And the snowbox will be right next door. The current status, I think this radon filter plant is now built and in the process of being commissioned. And we've taken delivery of the fridge. We're in the process of starting to test and move things to Snow Lab over the next year or so. As far as our long-term goals in the Super CDMS collaboration, but with Snow Lab, this is a breakdown that was put together recently. We already have limits from the R&D detectors and from Sudan that cover this whole space of, it's basically all of particle dark matter, including bosonic absorption down to 1 eV, and then electron recoil in the sort of 500 keV to 1 GeV range, as well as traditional NR up to a TeV or so, although, you know, above 10 GeV, it's not going to be necessarily all that competitive with the xenon experiments. But the projections that we've been showing for a while, we expect to have world-leading sensitivity down to about 500 MeV with the nominal Super CDMS Snow Lab payload. But the plan is sort of hybrid. You know, this will be the first run, and as we go forward, we will start to integrate more R&D detectors. So the high voltage detectors should drop in threshold, and that will gain us a better background discrimination as well. There's still R&D going on to the ionization readout, and then there's a lot of R&D going on to severely dropping thresholds down to below 100 millieV, and then small arrays of those detectors can cover a much lower mass space. So this is a cartoon, but it kind of shows you the various directions that we're going in, and the picture we're gonna be pitching for Super CDMS Snow Lab to the community as part of the Snow Lab, the SNOWMAS process. So summary, I talked about a lot of things. We're doing a lot of things. That's, if you come away with one impression, there's a lot of us, we do a lot of things, we do a lot of R&D, and we now have a really nice process for taking the R&D and getting dark matter science out of it. So we are seeing lots of backgrounds at low energy. There's a lot of follow-up underway. I'm pointing, Yoni Khan gave a nice talk about phenomenologically interpreting some of these excesses yesterday, and Lauren Su is giving the overview talk next week on dark matter in general, and she'll talk a little bit about the status of these excesses in the dark matter community. Look out for a bunch of new results, especially this 9 eV threshold result in the next 6 months. The Snow Lab detectors will substantially improve exposure, And they're going to benefit especially from what we learn about these new low energy backgrounds and about charge leakage. And then also, I didn't discuss in a ton of detail, but we have a lot of calibration programs underway to understand nuclear recoils. So the charge yield below a keV, especially down to 100 eV and less. And the first of those results should also be coming out by the end of the year. This was running the HVEV detector in the tunnel neutron beam. Yeah, so that's all I have. I know I went a little past the 20 minutes that I had for talking, but there's a couple minutes for questions, I think.
Thank you very much, Noah. Yes, there are a few minutes for questions. Bjorn? Bjorn, if you can unmute, you will be.
Sorry, I'm always double muted. Noah, hi, this is Bjorn. In this low energy nuclear recourse regime, how do you calibrate this and how well do you understand charge propagation there?
So you're talking about this new result here?
Mm-hmm.
Yeah, so this actually has nothing to do with charge. This is just a pure phonon readout. Okay. So the charge is, the bias is 0 volt and the charge just recombines almost immediately. So we're just getting, the tens of thousands of phonons collected in the phonon sensors. The calibration, like I said, we have these 5 lines. We have other ways to quantify the nonlinearity in the energy scale of the detector. So there's a lot of validation plots that we did. There's one in the paper showing that there is nonlinearity, and we've linearized this as much as possible. Part of the reason for the follow-up with the HVEV detectors is we can actually calibrate the energy scale with the laser. So we can get arbitrary data points below 1 keV. And that's going to be the main cross-check on whether there's any residual nonlinearity in the spectrum below a keV. So we are fairly confident that this has been properly linearized, but just like most of the other low nuclear recoil searches, we have this uncertainty of not really having a ton of calibration below 1 keV. And so we're working on strategies to bootstrap that.
Okay, thank you.
Chelsea, if you want to go next.
Thank you. I had a question. Could you go back to, I think it was slide 16? Yes, this, please. Yeah, I was just wondering, you mentioned Poisson counting method is less sensitive to systematic uncertainties. Why is that? I'm just curious.
So this is sort of to explain why the run 2 result here is slightly worse than the run 1, but the spectrum is the same. So what we're saying here is that essentially we've smeared in the run 1, the background is smeared enough that you have a broad Gaussian, you can kind of find with the optimal interval method bins where the natural fluctuation gives you a slightly better sensitivity. Because we're so quantized here, you can see the dark matter model for the run 2 spectrum has these sharp peaks. And so you can't really play games with the events in between peaks in the same way you can with a lower resolution detector. Okay. Yeah, so that's basically the resolution is good enough that we can literally just say, we expect the signal to be quantized. We look within 3 sigma of a peak and we just do a counting experiment.
I see, okay, thank you.
So if no other question, I would like to thanks Noah for the nice talk again, and we can move ahead with the next speaker.
Okay, that's my Zoom info, by the way, it's in the slides.
Thank you, Noah.
Thank you. So we have Simon Beal as the next speaker on the dark matter results from the at Snow Lab. And if you can share your slides as well. Perfect, thank you.
Thank you, Katerina. So yes, I'm going to talk about the latest results from Deep 3600 at Snow Lab. Deep collaboration has 95 researchers from 9 countries. And so we're still growing as a collaboration. About half the collaborations from Canada, and the other institutes are listed here. What we're looking for is this kind of signal. Obviously, the sun, as it goes around the galactic center with the Earth in tow, sees a headwind of wind particles. And so we're hoping to detect these dark matter particles in our underground detectors on Earth. And we go underground because we want to shield our detector from cosmic rays. And so there's this 8 order magnitude decrease from surface counts in terms of muon flux to going to Snow Lab, which is one of the deepest laboratories in the world. And so DEEP is located in Cube Hall, which is here on this map of Snow Lab, located right here. And so you can see the snow detector, which now upgraded Snow Plus. This is going to be DEEP right here. And if you haven't seen Snow Lab, if you haven't visited, there's a virtual visit on the Outreach website that I highly recommend. And so it's on this link here. And so I'm going to show a few pictures of DEEP during construction, so you have a clear view of the detector. DEEP is the largest acrylic cryostat ever built. Here you can see the installation of the neck of the detector. This is going to be important later. And on each of these spots here, 255 of them, there are light guides. So this is shown with the light guides installed in figure A here. And then reflectors were installed on each light guide. And then PMTs were bonded looking inward in each of 255 channels here. And after backing foam insulation and a steel shell installation, and also muon veto PMTs looking outward, the detector looked like this. And then we filled the water Cherenkov veto. You can see here on the left. So this is about a 10-meter veto that you can see here. All the details are available in our detector publication here. It was published in Astroparticle Physics. DEEP stands for Dark Matter Experiment Using Argon Pulse Shape Discrimination, with a design mass of 3,600 kilograms of liquid argon, hence the name. And the goal is really to detect dark matter particles colliding with argon nuclei. And so these dark matter particles come through the Snow Lab over Berlin into the liquid argon detector, inducing nuclear recoils. And then if they do, if dark matter exists and is detectable, these nuclear recoils would show up in excitations of the argon into the dimer excited state. And this dimer excited argon 2 de-excites, leaving a 128 nanometer photon. This is too high energy for our PMTs to detect, too low wavelength. And so we shift the wavelength using a layer of TPB right on the inside surface of the acrylic vessel. And what we actually detect are the 420 nanometer photons going up the light guides into the PMTs. And so there are two DEEP 3600 data sets. The first field data set that was collected in August 2016, and the dark matter results were published in PRL. And the second fill is actually has just ended in March 28th, 2020. So what I'm going to be showing is the results of the first year analysis, so November 2016 to October 2017, using this much liquid argon, and that was published in the Physics Review D. I'm also going to show new interpretations in terms of non-relativistic effective field theories that are being shown here for the first time. And so this is the lifetime of the detector over this whole second fill campaign. As you can see, our dead time is very low, shown here in white, around 3%. And then our radioactive source campaigns are shown here in pink. We're still taking data. So we've now emptied the detector to reach a safe state because of the COVID pandemic, but we're still taking data in gas argon and vacuum, and this informs our background model for the full data set analysis. We have a very good model of liquid argon scintillation and TPB emission, and also PMT after pulsing effects. Basically, when liquid argon de-excites, there's this singlet lifetime, which is very prompt, and the triplet lifetime, which is at a much longer time scale. And this is critical in terms of distinguishing nuclear recoils from electron recoils. The full pulse rate model has been published this year. You can look here for more details. And the key point here is that electron recoils or beta decays emit more late light compared to the prompt light in this window. compared to signal-like nuclear recoils that you can see here, where there's a higher ratio of prompt light to total light in the event. And so F prompt is the variable that we use here, which is the prompt fraction of the light. And you can see it in a 1D histogram here. And so in this neutron source calibration data, you can see how neutron nuclear recoils created this pink line here, including the gamma emissions. That is well modeled with data, whereas argon-39 argon-39 beta emissions created this shape here. And so we have a very good parameterization and understanding of pulse shape discrimination in our detector. And taking a cumulative distribution function from this data set without calibration source, we get this plot, which is the CDF of F prompt for a sliding cut, and demonstrating a world-leading PSD performance of 10 to the minus 9 for 50% nuclear recoil acceptance. More details in our paper here. And so looking at the events that we do detect, so F prompt here is shown here on the y-axis compared to the number of photoelectrons detected. And so in what we call the electronic recoil band, you see this argon-39 again here. At higher energy, these are gamma decays causing these events. In the nuclear recoil band, we see full energy alpha decays. But then some alphas are attenuated. Some neutron scatters can create lower energy events. These are mainly the backgrounds we need to quantify the most, because the dark matter region of interest is right here at low energy, high F prompt. And so focusing on the electromagnetic background band, so the lower band here at first, you can see here a very good model for these backgrounds. The argon-39 spectrum is shown here. And then we have the potassium-40, thallium-208 peaks. This shoulder here is dominated by argon-42, potassium-42 decays. And so this provided the world-leading measurement of the activity for these decays in atmospheric argon. In terms of the nuclear recoils, neutrons can that predominantly come from alpha N reactions in the PMTs can scatter around. Some of them, so most of them will be absorbed in the foam and the acrylic, but some of them can reach the liquid argon, where they cause nuclear recoils, before they capture either on hydrogen or argon-40. When they do capture and we see the gamma, we can reject the event. Otherwise, this allows for defining a control region where we can have data-driven estimate of neutron background. And this estimate is in agreement with our bottoms-up estimate, taking material assays, or PMTs, for example, as input. In terms of alpha backgrounds, the takeaway here is that we have a very good model. Our model describes very well the data that you can see here in the black crosses. And so the different components for the model are shown here in color. This is for alpha decays in the bulk of the detector. And so because all the energy here is deposited in liquid argon, these are much higher energy than potential dark matter interactions. And so this has no impact on the dark matter search. In terms of surface alpha backgrounds, there is this tail here going to lower photoelectrons detected. This is because a lot of the energy can be deposited in the acrylic or the TPB before being detected. And potentially this leaks into the dark matter region of interest, but fortunately, these events reconstruct right at the surface of the detector. And so this requires very good position reconstruction, which is the topic of this slide. And so in DEEP, we have two main algorithms that are complementary. There's one that's PE based, in that more photoelectrons are detected closer to the event. If you can imagine a surface event, most of the photons will go towards the nearest PMT. And so using the full 10 microsecond event window, we can have a very good reconstruction based on just on the pattern of detected signals in the PMTs. The other one is time residual based. And so based on the time of flight of the photons, photoelectrons will be detected earlier, closer to the event. And so using the first 40 nanosecond of the event, we can use a likelihood fit to the time of arrival distribution detected in the event to get a reconstructed position. And so both of these algorithms are reconstructing the events very well. For illustration, this is the reconstructed radius, histogram as a function of reconstructed radius, and the contained liquid argon mass based on our observation of argon-39 events. And so you can see there's very good agreement between the results from our fitters versus the analytical calculation for the contained liquid argon mass at a given radius. Our fiducial radius here is 630 millimeters in reconstructed R. And this is far enough from the surface, which is at 350, given our resolution of 30 to 45 millimeters at the fiducial volume boundary. This is very far from the actual surface. And so the leakage of surface alphas is very small, as shown here. NEC alpha backgrounds, on the other hand, are a more challenging, unexpected background, unexpected during the design of the detector, that ends up being very significant in deep. And so what's happening here is that in these flow guides, the liquid argon that's being cooled down drips from the inner side here, and then there's gas argon from evaporation that comes out here in the outer part of the flow guide. This leads to condensation on these cold surfaces. And so when there's a polonium-210 decay on one of these surfaces, sometimes for some topologies, the light will be shadowed just enough to show up in the low energy, high F-prompt WIMP region of interest. And so this is very signal-like and results in a particularly challenging source of background events. But by now we have a good simulation, a good model of what's going on. And this is shown on this slide where you can see these. So what's shown here is a reconstructed Z, vertical position in the detector, versus photoelectrons detected. And the smoking gun is really these arms feature here that are seen in the data. And so on the left, this is simulation from a model. On the right, this is data. And you can clearly see the same features here. And so this allows for a template fit using multiple control regions defined here in blue, and constraining separately the contribution from the outer flow guide and the inner flow guide surfaces, as shown here in this fit. There's also an extra source of background that we're actively investigating. By now we know what it is, and it'll feature in our next dark matter publication. This is shown here in red, and we have a better model than flat now, but this is what has been published so far. So for rejecting these NEC alpha backgrounds, we developed a dedicated event selection. One feature that helps a lot is that we have NEC veto wavelength shifting fibers here on top of the detector. And so in events that come from the NEC tend to lead to excess lights. And so we apply in what we call the NEC veto based on light in these fibers that are detected with 4 dedicated PMTs in the NEC. When there's a NEC event, there's also excess light in the top rows of the PMTs here due to reflection on the liquid argon surface. This also results in early light in the top rows of PMT, so we have cuts to reject those events. And also crucially, our 2 position reconstruction algorithms disagree when it's an actual NEC event versus when it's a true scintillation event from the liquid argon bulk. Shown here is a delta Z between the time-based and PE-based reconstruction algorithms for a WIMP simulation shown in green, argon-39 data shown in blue. So you can see there's very good agreement between our fitters here, but then for NEC events, this disagrees. And so this allows us to place a cut on this quantity. And so overall, there's one last handle, which is pulse shape discrimination. These NEC alpha our events are at truly higher energy. It's just that the light is shadowed. So this results in slightly higher F-prompt, which is shown here in the red band, compared to actual low energy recoils, which are slightly lower. So this is the green band that is shown here, again, in F-prompt versus PE. And then because of pulse shape discrimination, the argon-39 backgrounds are much lower in F-prompt. And so this is our region of interest shown here in black. And this is our acceptance, and our background budget for the 231 live day analysis is shown here, which is, as you can see, dominated by these NEC alpha events. And so the critical moment was Was dark matter observed in the first year of data taking? Nope, we saw no event in the fiducial volume here. As expected, there are some surface events here shown in green, and there are some events reconstructing at lower radius. These can be neutrons or surface misconstruction that are closer to the surface here. But there's no event observed here in the signal region, whereas we have significant WIMP acceptance. And so this is what we published last year and resulted in this limit shown here in red. Where it gets more interesting is our recent reevaluation of these limits for other sets of hypotheses beyond the benchmark. And so what's shown here, and it's shown at this conference for the first time, is variations in the speed distributions for dark matter compared to the standard halo model. And so the black line that you can see in each of these plots is the same. It's the distribution that's expected from the standard halo model, which is the benchmark that is used in most publications. But then the variations from the SHM according to different possible structures in the galactic dark matter halo are shown here. And so, for example, in what's called Gaia Enceladus or the Gaia sausage, if we vary the dark matter content to being, let's say, up to 70% in this structure, that's the difference in the speed profile that we would get here. And similarly for other possible substructures in the dark matter halo in the galaxy. And so based on these variations, we can recast our null result. The standard halo model is shown here in black, but then the other ones based on different substructures are shown here in color for different groups and also for Gaia Enceladus. It's also noteworthy that for isospin violating dark matter couplings, and so without assuming the same coupling to protons versus neutrons, DEEP is actually word leading for a region of the parameter space. And then we also investigated in a more general non-relativistic effective field theory framework, where instead of taking just the operator O1 as typically used in the benchmark, we considered other effective field theory operators here, O11, O3, O8, O5. And here you can see the same limits on the spin-independent dark matter cross-section as a function of dark matter mass. And what's the colored band here is the variation for more dark matter, let's say in the S1 dark matter halo substructure. This is for a retrograde stellar stream S1, where you can see the delta sigma in the limit versus sigma in the standard halo model. So you see these variations here for a prograde stellar stream. It goes in the other direction. And so what I've shown you so far is our published dark matter search from our first year data set, November 2016 to October 2017. But we have now a lot more data collected, 80% blind since January 1st, 2018. And so now to improve the sensitivity using this data set, we have developed 3 multivariate analysis algorithms specifically targeted against NEC alpha events. So what's shown here is the neural network score for nuclear recoil, shown in blue, versus NEC alpha events, shown here in orange. So there's very good performance. And then this is also being validated in data. And here's shown good agreement in the score between our Argon 39 event simulation versus real events. And so now we're validating all 3 of these algorithms and looking at all correlations between input and output variables to make sure we can use them in the dark matter search. And we're going to re-optimize our dark matter candidate event selection to be especially sensitive in our 3-year data analysis. The main upgrades that are coming forward, and now that we've emptied the detector, is that we have an ambitious hardware upgrade program. So the main objective is to limit and mitigate these background sources in the experiment. And so we're replacing the NEC. We're also going to cover the new NEC with a slow wavelength shifter to remove the NEC backgrounds with PSD, and keeping the NEC warm with an alternate cooling system. And so this should be the end. We should have a NEC background free exposure starting in 2021. And we're also dealing with this other source of background that I alluded to. And so the current status is that these repairs are going to take place in the coming 6 months. And we expect new dark matter search data in this upgraded detector starting in 2021. And so this sensitivity here would be even improved compared to our current data. And this will also inform the design of next generation liquid argon dark matter experiments. I'm out of time here. I just want to advertise the Global Argon Dark Matter Collaboration. DarkSide and Deep and MiniClean and RDM collaborations have joined forces towards DarkSide 20K, as was explained in Luigi's talk yesterday. And so the DarkSide 20K technical design report is in preparation, but this experiment is projected to be extremely sensitive to spin-independent dark matter interactions with nuclear recoils. And we're also working in earnest towards Argo, the multi-100-ton liquid argon detector, to reach the neutrino floor. And so in conclusion, we're looking for dark matter with Deep 3600. We have an excellent detector performance, and we're going to analyze our full 3-year data set using a multivariate analysis. There's a lot of new searches and measurements that I haven't talked about. There's a search for multiply interacting massive particles. There's analysis of the muon flux at SNOLAB. There are argon-39 specific activity and half-life measurements coming up, and a search for solar axions, just to mention a few. And so we have an ambitious physics program with our rich data set, and are going to perform a hardware upgrade to be even more sensitive to dark matter going forward. Thank you.
Thank you very much. It was a really interesting talk. And there's any questions from the audience? Not seeing any, so maybe I will ask one. So I'm wondering about your collaboration, the Argon collaboration, and where that is going. So what kind of lab support, if you're looking for any lab support, are you planning to be based a specific lab for the tests, or?
Do you mean for R&D or for the experiment? The experiment DarkSide 20K will be at NGS, and then we're planning on Argo at SNOLAB.
Okay, so, and then the other question is that you're, because it's a sort of multi-lab collaboration, you're doing the R&D separately or together?
Yeah, no, separately. So there's a lot of R&D still going on and finalizing the design of DarkSide 20K. We're in better shape now than ever, but there's still R&D that was mentioned in Luigi's talk going to for the SIPM that's almost done now, but also for coatings, for TPB deposition, for the acrylic vessel that needs to be built. So we know a lot of that, how to do that from the previous experiments, but going at such scale, there's in the different universities and national labs, there's a lot of effort going on to meet our schedule for DarkSide 20K. And then for Argo, there are even bigger questions. So for example, is it going to be a single phase detector, or is it going to be a dual phase TPC? And so these are design studies that are also taking place.
And the DarkSide LM, how is it connected to this effort?
Yeah, so DarkSide Low Mass is a dedicated detector looking to exploit the effects that Paolo just mentioned previously in the session. And so with a bigger mass, we're planning to reach a very good sensitivity at low mass.
And it's still part of anyway, the same collaboration somehow? It's
the same collaboration, different detector, yeah.
Okay. Thank you.
Thank you.
Any more questions?
So if no other question, maybe we can move ahead with the next speaker of the session. So Sergio Palomares Ruiz, if you want to start sharing the slide. And he will talk about probing heavy dark matter with the 6-year ICECube hazy data. Okay, so we can see you, but not the slide yet. Okay, great. Now, yes, thanks.
Okay. Let's see. Now you see the full screen, right?
Yes.
Okay. Okay. So thank you. And yeah, I'm going to well, thank you. Good afternoon, good evening, and good morning to everyone. And I'm well, being the last talk of the session, and probably I think I was of the day. I'm going to completely change gears. I feel a bit of an outsider in this session, but I'm going to completely change gears. So we've heard during this afternoon, well, this afternoon for me, many talks on direct searches of dark matter in the GeV regime, and I'm going to talk about detection of dark matter with very heavy dark matter with masses in the range between 100 TeV to a few PeV. And I will not be talking about the detection of dark matter, direct detection of dark matter, but of indirect detection, and in particular of indirect detection with neutrinos and with the ICHEP neutrino telescope, and in particular with the HESI data that we'll explain next. So I will say a few words about ICHEP detector and the astrophysical neutrino flags observed by ICHEP and how we can use it to search for new physics and in particular to search for dark matter. Okay, so the ICHEP neutrino detector, probably you know, and I'm sure you know, and I don't even have a slide for that, but it's a gigantic detector placed at the South Pole. Is 1 km³ of instrumented material in the ice. And the detection principle is the detection of the Cherenkov light emitted by the charged particles, which are produced by particles in neutrino interactions, either inside the detector or outside the detector. And this is why we have like two grand classes of events. Then there are subcategories, but these are the two types of searches. So one is using contained events, in which case the interaction vertex of the neutrino happens inside the detector. And this is the type of events that I will be discussing in this talk. HESI events stands for high energy starting events. And this is a sample of events that have the vertex inside the detector. And then we have through or muon events, which are produced by muon neutrinos that go through the Earth and produce a muon lepton outside the detector, and this muon goes through the detector, and this is why they are called through muons. And one can do a fit of the data, trying to fit the astrophysical neutrino flags, which is way over the atmospheric background and many sigma already. With the number of years that ICHEP has been collected data, this is settled at many sigma. So one can do a fit of the observed astrophysical spectrum with a simple and featureless power law flux. That is what one would expect naively and roughly from astrophysical accelerators. And it turns out that if one does this kind of fit, for instance, with the contained sample, like HESI sample, one gets something like this orange contours, this is the normalization of the spectrum, and this is the spectral index. So basically one gets an index which is very, very large, very soft spectrum, an index very close to 3, which is much softer than what one would expect naively from an astrophysical accelerator. What happens is if one does the fit with the through in sample, then one gets this blue contour, and that means that it represents a much harder spectrum, much in agreement with the expectations, the theoretical expectations, something like a spectral index of 2.2, 2.3, something like that. So this tension between these two samples, and here this is another result from a different sample, are in tension at more than 2 sigma, I would say close to 3 sigma. So this might be more than a tension on the data samples or anything. It's really maybe a tension on the input that we are using. So maybe the simple power law, featureless spectrum is not the end of the story, and the spectrum it has more structure, and maybe we need more components. And actually, the rest of the talk will be more along those lines to having what is the implication of having more components, and if we can fit the data better than with a single component. So how can we use this data, all these neutrinos observed by ICHEP to search for new physics? Basically, it's using the different observables in ICHEP. One can use the energy, which is measured in ICHEP of these events. One can use also the arrival direction, so the angular spectrum of the neutrino flux that reaches ICHEP. And one can also use the flavor composition of this flux, which is a unique, let's say,
observable with neutrino detectors. And then one can also use the arrival time of these neutrinos when compared with other messengers. Here I have many different scenarios that are affected by or affect different observables. But in the case of, I will be concentrated on dark matter decays, and I will make some comments on annihilations. The observables that are mostly affected are the energy spectrum and the angular spectrum. A little bit on flavor, but not really important. These are the two main. Energy and angular direction is the most important observables. So let me talk about dark matter decays next. So actually, just soon after the first two PeV neutrinos in ICHEP were observed, there was this paper by Feldstein and collaborators where they posed the following question: can these highest energy PeV neutrinos be explained by heavy dark matter decays? And actually, one can do a simple back of the envelope calculation and realize that to explain PeV events, one needs PeV dark matter. So for this mass, one will need a lifetime of the order of 10 to the 28 seconds or so, which is kind of reasonable or can be achieved from theoretical models. And soon after this paper, there was another paper by Smiley and Serpico, where actually they were not trying to explain only the highest energy events, so these two PeV events, but they were considering the possibility to explain all the IceCube neutrinos on top of the atmospheric background to be explained by heavy dark matter decays. They used 2 years of HESI data, and they consider different combinations of soft and hard channels and managed to get a reasonable fit of the astrophysical neutrino flux in terms of dark matter decays. Actually, this qualitatively has not changed much along the years, as I will explain in this talk. Okay, so this was the thing, and so what are the neutrinos from dark matter decay coming from? So we have two components. We have one galactic component, which depends on the density of the dark matter, so it's more concentrated towards the galactic center. And then we have an extragalactic component, which is isotropic. So this, the sum of these two components, of these two contributions, produces an angular anisotropy on the signal, unlike what happens with the expected isotropic astrophysical signal. And here in these two figures, I'm showing you just different neutrino fluxes expected for different decay channels. So for instance, on the right, I'm showing you the decay, dark matter decays into leptons, and that produces very hard channels. Unlike what happens if dark matter decays into quarks, in which case the neutrino spectrum is much softer, peaking at lower energies. And this is just something to keep in mind for the rest of the talk. Decays into quark channels produce soft channels, soft neutrino spectrum, and decays into leptons produce a hard neutrino spectrum. Okay, so after these few early papers on proposing the possibility that part of all of the neutrino spectrum observed by IceCube could be explained in terms of dark matter decays, there were a number of papers investigating the possibility that if the angular spectrum was compatible with what was seen. As I just mentioned, the dark matter decays would have some angular anisotropy towards the more enhanced towards the galactic center. And there were a number of papers saying that, asking this question, like, are neutrinos from dark matter decays compatible with the angular distribution of the IceCube events? And depending, there were different analyses, as I said, using different samples, different assumptions. So they got slightly different conclusions, but they were not significantly different. Basically, all the conclusions are similar within, say, 1.5 sigma. So we cannot really tell which one of the two options is better, just with the current statistics and using these two hypotheses. Okay, so, but so far I've only considered the possibility that these events could be explained by only dark matter decays, like in the Smiley and Serpico paper. But if we only explain part of the spectrum, we need to explain the rest, and the rest would be explained with astrophysical neutrino flux, the usual expected astrophysical neutrino flux. As far as I know, the first analysis that included dark matter decays and an astrophysical neutrino flux trying to fit the HESI data was this paper by Atri Bhattacharya, Halsey Green, and Ina Sarcevic, where they fixed the astrophysical index to 2. Then there have been other analyses doing limits on monochromatic decays. By no means this This list of papers that I mentioned here is exhaustive. These are just a selection of some of the early papers on this. There have been other analyses of other samples, like for instance, the MESI sample. This is similar to the HESI sample. HESI sample starts at 10 TeV and goes beyond the PeV range. And the MESI sample goes down to 1 TeV. In this analysis, the authors fix the astro index, but they also consider astrophysical flags. One can also do a 6-year analysis of HESI, which is what I will present. In this analysis, it was done fixing the astrophysical index, which I will leave free in all the analysis I will present. And then also one can, in principle, use the 7.5 years of HESI, which have not been fully released publicly. And this was done in a paper after the paper I will be presenting today by this group. And they also added some priors on the through OME sample. The results are very similar, actually, with what did you get with 6 years. But let me move on. And but apart from the neutrino spectrum, if dark matter decays, would also be accompanied by a gamma ray spectrum. And however, gamma rays with energies about, say, 10, 100 TeV, for those energies, the universe is not transparent anymore, and actually gamma rays interact with the background radiation, mainly the CMB, and produce E plus and minus pairs, which produce further gamma rays via inverse Compton onto the CMB photons. And then until energies of these gamma rays fall below, say, 100 GeV or so, for which this cascade process cannot proceed any further because you don't produce these E plus and minus pairs. So, and then one can test if the neutrino flux and the expected flux of gamma rays at high energies are associated with this neutrino flux, what is the gamma ray flux below 100 GeV that would be expected from this cascade process, and one can search for that in experiments like Fermilab. One has to take into account that this applies, what I just said applies to extragalactic signal, but in the case of the galactic signal, there is different absorption. Actually, full absorption is not guaranteed, and actually one could expect to see gamma rays in the TeV range from dark matter decays in the galaxy, and this seems to be okay with current detectors. But if one does, for instance, analysis of, for instance, the dark matter decays into BB bar, taking all this into account, it seems there is tension. This is what one would expect from ICHEP data, and the red lines are the limits from gamma ray. Anything below the lines are excluded. So it seems that for some channels, there is tension between gamma rays and neutrino data, if one wants to interpret the data in terms of dark matter decays. And for the rest of the talk, whenever I talk about gamma ray limits, I will be using those from this paper. Although let me point out these other papers, and in particular this last paper by Isiwara et al., which updates the limits from this paper and extend with further messengers. And let me just comment another paper which was suggested the possibility that there was a high galactic latitude TeV signal and gamma rays that could be the counterpart of a neutrino extended source from the galaxy, and that could be, for instance, a signal from dark matter decay from the galactic halo. But I won't say any further on that. So let me move on to the analysis. And before getting to the 6-year analysis, which is what I will be presenting, let me show you what is the results from the 4-year analysis, for which we also wrote a paper, and see how the results evolve in time. So, for instance, in the case of dark matter decays into quarks, you see that we need short lifetimes to explain part of the spectrum. And let me just stress, I didn't say this, and in all this analysis, I will take a possible dark matter decay contribution and an astrophysical power law flux contribution. So we are fitting both contributions with all the parameters involved. So in the case of dark matter decays into quark channels, you see a soft spectrum explaining the 100 TeV. This is the black line is the best fit for dark matter decays, and the green line is the astrophysical flux, and the total one is the magenta one. So you see that for dark matter decays into quarks, we explain the low energy data around 100 TeV or so, but the problem is that we need short lifetimes, and that produces too much gamma rays, as I will show next. And the good thing is that this explaining the low energy events in terms with dark matter decays that leaves the high energy events to be explained by the astrophysical spectrum. So that requires the astrophysical spectrum to have a power law of index of the order of 2, 2.2, something like that, which is fully compatible with theoretical expectations and what it is seen by the through immune sample. Then if we go to harder channels, like annihilation, decays into gauge bosons, then we get longer lifetimes, that is good. And then these decays are meant to explain the highest energy part. So that leaves the low energy part, around 100 TeV, to be explained by the astrophysical spectrum, which requires a very soft, with an index much larger than 3, something like 3.5 or so for the best fit scenario. And just let me stress about this panel here on top right. Here is the allowed regions for the case of decays into W bosons. This is the lifetime versus the mass. And you see that the best fit lies within the PeV range, but you see these 1 sigma regions around the 100 TeV regime. And this, I want you to keep this in mind, because this will become relevant when we add the 2 more years of data. Here I show you the analysis, the results for harder channels, decays into leptons. And you see here, we get very long lifetimes with masses in the PeV regime. So that explains the high energy part of the spectrum in terms of dark matter decays, and the low energy part is explained by a very soft astrophysical spectrum. And that happens for all these hard channels. Here I'm just showing you, just for reference, the different channels that we consider of dark matter decays. Here I show you the best fit results and the typical values of the astrophysical indices. Typically for soft channels, we get astrophysical index more in agreement with the through immune sample. When we go to harder channel, that we need the astrophysical spectrum to explain the 100 TeV regime in the ICHEP data sample. So that requires a very soft astrophysical index. But overall, you see that the delta chi-square for all the channels with different energy regimes, energy samples that we consider, are within a few units. So all these cases give a reasonable fit only using neutrino data. So one can also set limits on this, and here I show you different limits. These are limits, dark matter decay into BB bar, this is W's, and these are the lower panels are into leptons. And the dotted lines are gamma ray limits, and anything below these lines is excluded. So you see that the gamma ray limits in the case of dark matter decays into quarks excludes the best fit parameters required to explain the ICHEP data. Actually, basically exclude the entire regions of 1 or 2 sigma, maybe 1 sigma regions required to explain the data. So this is why that decays into quarks, into soft channels, is in tension with gamma ray limits. However, and this is important to note, when we go to harder channels, actually we have the neutrino limits are the best limits that one can get, better than gamma ray ones for relatively hard channels for masses about 100 TeV. And this is kind of a take-home message. Okay, so let me move on because I'm running out of time. This is the 6-year analysis. This is for the dark matter decays into W's. This is the best fit, but now we have no 1 sigma region here, and all happens at the 100 TeV regime. Now the dark matter wants to explain, dark matter decays wants to explain the 100 TeV regime, and that requires also an astrophysical spectrum, which is very hard, which are a power law index compatible with through immune sample. And the reason for this is that in these 2 extra years of data, there is no PeV event, but only sub-PeV events, which contribute in this regime. And that is why dark matter wants to explain that region. We have here also for hard channels, still we have the best fit at the highest masses, but also getting more confidence into the 100 TeV regime. Here I show you the different results, similar things when we compare among the 6-year analysis, and even when we compare with the 4-year analysis, everything stays within, let's say, a couple of sigma. We can get limits, and actually the limits are very similar with the 4-year results. So I will not say any further comment on this. And one can actually explain all the data along the lines of Serpico and Smiley, and trying to explain all the astrophysical data with only dark matter. With 2 years of data, that could be done. With 4-year data, we did that, and that could be done. With 6-year data, that could be done. But the problem with this is that to explain all the data, we need a dark matter of a mass of PeV, of a few PeV, and we need to explain the low energy data, and for that we need a soft channel to contribute a lot. And actually, you see 90%, 97% of the branching ratio has to be into a very soft channel that produces too many photons, and that is in tension with gamma ray limits in general. And just a few comments before I finish on dark matter annihilations. One can also consider the possibility of explaining the data with annihilation instead of decays. And here, the dark matter signal from the galaxy depends on the square of the density, so it's more focused towards the galactic center. We have an extragalactic component, and here we have an uncertainty coming from a clustering factor that depends on how dark matter clusters and halos of different sizes at different redshifts. And for that, we introduce a new parameter to gauge the contribution between the galaxy and the extragalactic contribution. One can do a back of the envelope calculation that was also done in the Felstein et al. Paper, and realizes that one would need a very large annihilation cross section to explain part of the data, which is above the unitarity limit, and from this point of view, loses interest. But one can do a phenomenological analysis, and this is what we did. We see that the best cases of this for the dark matter annihilations is in W bosons, explaining the low energy data, 100 TeV, and you see qualitatively similar. That in the case of decays, 100 TeV, dark matter annihilation to explain this, and then we require astrophysical flux much harder in agreement with the through result. But remember, in all this analysis, I'm not imposing any prior coming from the through sample. This comes naturally from the HESI sample. Well, there is no significant extragalactic contribution that is needed, but this is not a big deal. These are the results, similar statements, but in any case, very, very large cross-section, way above the unitarity limit. Here are the limits on the dark matter annihilation cross-section. The unitarity limit is 1 or 2 orders of magnitude, at least below the values in these plots. Well, I will not comment on this because this is not that interesting, and I'm running out of time. This is just my last slide before the conclusions. I mentioned at the very beginning that we have 7.5 years of HESI data, but this data has modified selection cuts, which are non-public yet. So this is why we didn't use them. But there are some preliminary analysis from the ICHEP collaboration itself, and the results are very similar to what I just showed you for 6 years of HESI, with limits around 10 to the 28 seconds for a large range of masses. So let me conclude. In addition to be produced by a standard mechanism, high energy neutrinos could be produced by dark matter decays, maybe annihilations. And ICHEP data is compatible yet with a contribution from dark matter decays. And actually, dark matter decays could explain the region around 100 TeV of the HESI data. And then we can have a hard astrophysical spectrum that explain the higher energy events in the HESI sample. And that would be in full agreement of the through sample, which is also sensitive to the highest energy part of the spectrum. And then finally, let me just stress that the neutrino data set the strongest limits on the dark matter lifetime for hard channels and masses around 100 TeV or so. Thank you.
Thank you very much, Serge, for the very nice talk. Are there any questions? I have just a curiosity. I'm very naive on, so what does how a different density profile might affect your result?
You mean the dark matter density profile in the galaxy?
Yeah.
Little, actually. We, as I mentioned, with the current data, distinguishing a purely isotropic signal from a signal with the anisotropy associated to for instance, dark matter decay is very hard with current statistics. It cannot be done at, say, more than, it's definitely less than 2 sigma. So barring the astrophysics, the profile of the dark matter within the galaxy would simply add some fraction, a small difference with respect to the decay. And we cannot distinguish that dark matter decay from a purely isotropic yet.
Okay. So are there any question or comment for this last talk? If not, I would like to thank Serge and all the speakers of the session. And I leave the last comment to Caterina. Thank you.
Thank you very much for the session and for contributing with both talks and questions. And we are obviously not done with dark matter. And we'll have another session tomorrow morning, starting bright and early at 8 a.m. in European time. The session tomorrow will be both the kinds of WIMP dark matter experiments, results, interpretations, and also sort of community building. So it's an interesting session for everyone. For tonight, some of the speakers have put up their Zoom link if they want to be found and they don't have anything else to do because it's kind of late as well in Europe. So you can click on the talk and see if there's a Zoom link below that. And I will be around for a little bit longer here in case there's any technical problems. But I think everyone who wanted to have their Zoom link up had their Zoom link up. Otherwise, we can even keep this one open for a while. And with that, I hope I didn't forget anything, Sylvia. I guess no. Okay, good. Okay, so thank you again, and see you either in the rooms of the speakers or tomorrow morning. Thanks a lot.
Thank you very much. Bye.